40 trillion kilometers. That's how far Proxima Centauri is. And getting there would be the most brutal thing our species has ever attempted. It certainly would end us before we got halfway there. Not because of the distance, not because of the cold. So why are serious scientists planning it anyway? What do they know that we don't? If you're the kind of person who wants to understand the universe a little better every day, make sure to subscribe to the channel. Now let's get started. First, you need a reason to go, and we have a spectacular one. In 2016, astronomers announced one of the most exciting discoveries in the history of planetary science. Using the European Southern Observatory's HARP spectrograph in Chile, a team led by astronomer Guillem Anglada Escudé detected a planet orbiting Proxima Centauri. They called it Proxima Centauri b. And this wasn't just any planet. It sits in what scientists call the habitable zone, the region around a star where liquid water could theoretically exist on a rocky surface. You know what else sits in a habitable zone? Before we get carried away, and we absolutely will get carried away later in this video, scientists are quick to point out that habitable zone doesn't mean inhabited. It doesn't even mean definitely habitable. There's so much we still don't know about Proxima b. Does it have an atmosphere? Does it have a magnetic field strong enough to protect it? Is it a barren rock, a frozen wasteland, or something else entirely? These are questions we're actively trying to answer right now. The James Webb Space Telescope has begun observation programs aimed at this system, and the European Extremely Large Telescope, a 39-meter mirror currently being built in Chile, may be our best shot at directly imaging the planet within this decade. But here's what makes it so extraordinary. This potentially rocky, possibly Earth-sized world is the closest exoplanet we know of. It's our nearest neighbor in the entire galaxy. And that proximity changes everything about what's possible. Speaking of proximity, if you've ever found yourself wondering how close our other nearest neighbor is, and how long it would take to actually reach it, I did a full deep dive on that too. On the card above, we explored how long it would really take to reach Mars. It puts a lot of these distances into perspective in a way that I think you'll find really eye-opening. The link is in the description and pinned on the comments. Now, back to our mission. The planet's been confirmed, or at least it's our strongest candidate. The science says, let's go. Where do we even begin? The first thing any mission planner tells you is this. Before you can think about getting there, you have to think about propulsion. What engine, what force could possibly push a spacecraft across 4.24 light-years in any time frame that matters to human beings? Let's walk through what's actually on the table. And this is where the science gets genuinely thrilling, because some of the ideas aren't science fiction, they're real engineering proposals backed by serious research. The most talked about near-term concept is called Breakthrough Starshot, announced in 2016 and backed by $100 million in initial funding from entrepreneur Yuri Milner, and endorsed by the late Stephen Hawking. This project proposes something audacious. Send tiny spacecraft, barely larger than a postage stamp, equipped with ultra-thin light sails, and accelerate them using a massive ground-based laser array. We're talking about a laser so powerful it would push these gram-scale starships to 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take approximately 20 years. 20 years, not 75,000, not 6,000, 20, of course, and this is the part that keeps physicists up at night. The engineering challenges are almost beyond imagination. You'd need a laser array producing something in the range of 50 to 100 gigawatts of focused power. The sails themselves would need to be just a few hundred atoms thick and able to withstand that kind of radiation without vaporizing. And the tiny probes would have to survive decades of travel through the interstellar medium, a vast, thin cloud of gas and dust, while being bombarded by high-energy particles and micrometeorites that, at 20% the speed of light, would hit like miniature nuclear blasts. And here's the kicker: even if all of that works perfectly, even if the probes arrive after 20 years of travel, the signal they send back home takes another 4.24 years to reach us at the speed of light. So from launch to first data received, you're looking at roughly 24 to 25 years minimum. Anyone who launches this mission will be in their 60s or 70s. If they're lucky enough, before they hear a single beep from Proxima Centauri, that's not a reason to stop. That's a reason to start immediately. But Breakthrough Starshot is a probe, a tiny unmanned microchip riding a beam of light. What if we're talking about something bigger? What if we're talking about human beings making that crossing? That's where physics really starts to push back on us, and in the most profound, almost philosophical ways. Because the moment you start scaling up, adding life support, food, water, radiation shielding, propulsion for an actual crewed ship, the energy requirements explode to numbers that are genuinely hard to process. A spacecraft massive enough to carry people and keep them alive for years would require propulsion technology we simply don't have yet. The most promising serious candidates: nuclear pulse propulsion, fusion rockets, antimatter drives, each carry their own extraordinary challenges. Nuclear pulse propulsion, studied briefly during the 1950s and 60s under a project called Orion, would essentially detonate a series of nuclear bombs behind the spacecraft to drive it forward. Studies suggested it could reach a meaningful fraction of the speed of light, but the technology is legally banned under nuclear test treaties, astronomically expensive, and would require breakthroughs in materials science to even attempt. Fusion rockets, which would use the same process that powers stars, are theoretically capable of reaching about 12% the speed of light, which would get you to Proxima Centauri in roughly 36 years. But sustained, controlled nuclear fusion has been one of humanity's most elusive engineering goals for over 70 years. We're getting closer. The National Ignition Facility achieved fusion ignition in 2022, a historic milestone, but a fusion rocket engine is still many generations of engineering away. And then there's antimatter. If you could annihilate matter and antimatter together, you'd release energy with an efficiency that makes nuclear fission look like a campfire. A theoretical antimatter engine could push a ship to half the speed of light, getting you to Proxima Centauri in under a decade. The catch? Antimatter is the rarest, most expensive substance ever produced by human beings. The total amount ever made in particle accelerators across the entire history of physics amounts to a tiny fraction of a single gram, and producing even that took staggering amounts of energy. We are nowhere near being able to make enough antimatter to fuel an interstellar ship. So here we are. We have a destination, an enticing, potentially rocky world orbiting the nearest star. We have ambition, we have some early-stage proposals, and we have physics pushing back at every turn, reminding us that the cosmos does not bend its rules for anyone. But here's the thing about human beings: we've always found a way forward. Every time a problem looked truly impossible, someone thought sideways, someone asked a different question, and that different question changed everything. We haven't even gotten to the most mind-bending part yet, because even if we solve propulsion, even if we build a ship capable of reaching a meaningful fraction of the speed of light, something strange starts to happen to space, to time, and to the people on board. Something that Einstein predicted over 100 years ago. Something that still feels like magic, even though it's completely real. What happens to time when you travel fast enough? What does your body actually experience during decades in deep space? And what would you find when you finally arrive, drifting in orbit around a dim red star 4 light years from home. That's exactly where we're headed now. Stay with me, because we're just getting off the ground. Let's talk about time, not in a vague philosophical way, in a real, measurable, physics-backed way that will genuinely change how you think about the universe and your place in it. When Albert Einstein published his special theory of relativity in 1905, he wasn't just scribbling abstract equations on a chalkboard. He was describing something fundamental about the nature of reality. Something that at first sounds completely impossible. The faster you move through space, the slower you move through time. Not as a metaphor, not as an illusion, as a physical fact measured and confirmed thousands of times in experiments around the world. We call it time dilation. And on a journey to Proxima Centauri, it stops being a physics curiosity and becomes one of the most practically strange and emotionally profound aspects of the entire trip. Here's how it works in plain language. Imagine you climb aboard a spacecraft and begin accelerating toward Proxima Centauri. As your speed climbs, 10% the speed of light, 15%, 20%. Time on your ship begins to slow down relative to the time being experienced by everyone you left behind on Earth. Not because your clocks are broken, not because something has gone wrong, but because that is literally how time works in a universe governed by relativity. The effect is small at lower speeds. At 20% the speed of light, roughly the target speed for Breakthrough Starshot, the time dilation factor is modest. For every 100 years that pass on Earth, about 98 years would pass on the ship. Noticeable in theory, but not dramatic in practice. But push that speed up. Get to 50% the speed of light, half the ultimate cosmic speed limit, and things start getting genuinely strange. Now, for every 100 years on Earth, only about 87 years pass on the ship. Push to 90% of light speed, and the numbers really start to separate. For every 100 years back home, only about 44 years tick by on the vessel. Get to 99% of light speed, and now you're down to about 14 years on the ship for every 100 on Earth. And at 99.99% of light speed, time on board slows to a trickle. A journey that takes 4.24 light years in Earth's reference frame could be experienced by the crew as just weeks or months. Think about what that actually means for a moment. It means, in pure physical theory, that a human being could board a ship, travel to Proxima Centauri, and return to Earth having aged only a handful of years, while decades or even centuries have passed back home. The people you left behind, your family, your friends, everyone you knew, would be gone. The world you return to would be unrecognizable. You would be a traveler from the past, dropped into a future you never lived through. This isn't from a movie. This isn't speculation. This is the confirmed mathematics of space-time. We've actually measured time dilation here on Earth using ultra-precise atomic clocks placed on aircraft and satellites. The GPS satellites orbiting our planet right now have to account for time dilation in their programming, or they'd give you directions that drift by kilometers every single day. The universe bends time, and the closer you get to the speed of light, the more aggressively it does so. Now, here's the part that turns this from a physics lecture into a deeply human story. Because all of that assumes we can actually get a human being to those kinds of speeds, and the moment we try, the human body starts to become the biggest engineering challenge of all. Let's start with radiation, not the Hollywood kind, where someone glows green and gets superpowers. The real kind, the kind that tears through cell membranes, breaks DNA strands, increases cancer risk, and degrades the central nervous system over time. Out beyond Earth's protective magnetic field and atmosphere, space is a constant bombardment of radiation. You've got solar energetic particles, high-speed protons thrown off by solar flares and coronal mass ejections. You've got galactic cosmic rays, incredibly high-energy particles accelerated by supernovae and other violent cosmic events, flying in from every direction at nearly the speed of light. And you've got the radiation environment inside the ship itself, as some of those particles slam into the hull and produce secondary radiation showers. NASA's data from the Curiosity rover's trip to Mars gives us a real-world baseline. During the roughly 253 days it spent in transit, Curiosity measured a radiation dose of about 300 milligrays, roughly equivalent to what a human would absorb over that journey. That's already a significant dose. And Mars is next door compared to Proxima Centauri. A crewed mission lasting decades would expose astronauts to radiation levels far beyond anything we've managed with current shielding technology. The longest any human being has continuously spent in space is 437 days, set by Russian cosmonaut Valery Polyakov aboard the Mir space station back in the mid-1990s. And even in low Earth orbit, still protected by Earth's magnetic field, extended stays cause measurable bone density loss, muscle atrophy, cardiovascular changes, vision problems caused by fluid shifts toward the head, and immune system disruption. We know this, we've studied it. NASA's twin study, which compared astronaut Scott Kelly after a year in space to his twin brother Mark, who stayed on Earth, gave us some of the most detailed data we have on what prolonged spaceflight does to the human body at a genetic level. What it showed was sobering. Scott's telomeres, the protective caps on chromosomes often associated with aging, actually lengthened in space, then shortened rapidly when he returned. His gene expression shifted in hundreds of ways. His cognitive performance showed measurable changes. Some of those changes reversed after he returned to Earth. Some didn't. Now scale that to a journey of 20, 30, or 40 years in deep space, far from Earth's protective field, far from rapid medical evacuation, far from any help at all. The radiation shielding required to protect a crew over that kind of time frame would need to be extraordinarily thick and heavy, which means more mass, which means more fuel, which means a harder launch and a slower ship. It's a web of interconnected engineering nightmares, each pulling against the others, and that's before we even talk about the psychological dimension. Because the human mind, as extraordinary as it is, was not built for this. We evolved on a single planet, surrounded by seasons and sunrises and other human beings. We are deeply biologically social creatures. We need relationships, novelty, nature, meaning, rhythm. Space exploration research has shown us again and again that isolation and confinement don't just feel unpleasant, they genuinely degrade mental health, cognitive performance, and group cohesion over time. The longest isolation study ever run was a simulated Mars mission called Mars 500, where 6 volunteers spent 520 days sealed inside a facility in Moscow, simulating the experience of a long-duration spaceflight. The findings were striking. Over time, the crew showed increasing signs of sedentary behavior, disrupted sleep, and psychological withdrawal. Even knowing it was a simulation, even knowing they could walk out, the pressure of the environment shaped them in ways they hadn't anticipated. Now imagine the real thing. You're on a ship. There is no outside. There is no sky, there is no wind, there is no smell of rain or sound of birds. There are a small number of human beings sharing an enclosed space, dealing with stress and fear and boredom and grief, with no hope of relief except the passing of years. The nearest human voice outside your ship is at least a light year away, and a message home takes years to arrive and years to get a response. What does that do to a person over a decade? Over 3 decades? These are questions space psychologists are actively working on right now. NASA, the European Space Agency, and research groups around the world are developing frameworks for crew selection, conflict resolution, mental health support, and habitat design, specifically for long-duration deep space missions. Virtual reality environments designed to simulate natural settings, AI systems built to provide therapeutic conversation, scheduled autonomy, giving crew members meaningful control over their own schedules. To preserve their sense of dignity and agency, it's genuinely moving when you think about it. Thousands of researchers, right now, are working to protect the inner lives of people who haven't been born yet, planning for the emotional well-being of astronauts who won't launch for generations. Because we understand, even now, that the journey to the stars is as much about what it does to a human soul as it is about engines and trajectories. There's another challenge we haven't touched on yet, and it might be the strangest one of all. What do you eat? A crewed ship heading to Proxima Centauri cannot carry 40 years' worth of food. The mass alone would be prohibitive, so any serious mission plan has to grapple with how to sustain human life using closed-loop systems, essentially creating a miniature biosphere inside the ship. Plants that convert carbon dioxide into oxygen, water recycled with near-perfect efficiency, nutrients grown, processed, and consumed in a continuous loop. We actually have meaningful research on this. The International Space Station recycles a remarkable proportion of its water, including, yes, urine and sweat back into drinkable form. Experiments growing food in space, lettuce, radishes, chile peppers, have been conducted aboard the station and have worked. NASA's Advanced Plant Habitat has produced crops under controlled conditions in microgravity. These aren't just experiments for science's sake. They're prototypes for survival, but a self-sustaining food system capable of feeding a crew for decades in a closed environment with zero resupply. That's a much more complex challenge than anything we've attempted. It requires a living ecosystem inside the ship, plants, microorganisms, nutrient cycles, water filtration, all functioning together with no margin for catastrophic failure for years on end. Some researchers have proposed that the most realistic long-duration missions might not carry humans in the traditional sense at all, at least not for the full journey. They propose suspended animation or torpor, slowing the human metabolism to a fraction of its normal rate, dramatically reducing food consumption, psychological strain, and even radiation sensitivity. NASA has actually funded early-stage research into therapeutic torpor for spaceflight. The concept involves lowering core body temperature and inducing a state similar to the hibernation some animals use to survive winter. 2-week torpor cycles, alternating with wake periods, could potentially allow a crew to cross the vast dark between stars while barely experiencing the passage of time. It sounds like science fiction. But it has real biological precedent, and it has real researchers behind it. The universe rewards patience and sometimes imagination, so we have time dilation bending the clock, radiation eating at the body, psychology testing the mind, nutrition demanding near miracles of engineering, and all of this is before the ship even gets far from home. Here's what I want you to feel right now, not discouragement, but awe. Because every single one of these problems is being worked on. Every single one of these challenges has brilliant people dedicating their careers to solving it. And every generation of science has looked at the impossible list and slowly, stubbornly, crossed items off one by one. We didn't just figure out flight. We went from the Wright brothers' first 12-second hop in 1903 to putting footprints on the moon in just 66 years. 66 years from barely leaving the ground to standing on another world. If that kind of acceleration in capability continues, and there's real reason to think it will, especially with advances in artificial intelligence, materials science, and our understanding of nuclear physics, then the timelines we're talking about for interstellar travel might be far shorter than they feel today. But let's stay grounded in what we know. Let's keep asking the hard questions. Because the most thrilling moment of this entire journey isn't the launch, or the cruise through the interstellar dark, or even the arrival. It's the approach. The moment the sensors on your ship begin to resolve the light of Proxima Centauri into something more than a point, when the data starts flowing back, and you begin to understand what is actually waiting for you at the other end of a 4.24 light-year crossing. And that's exactly where we're going next. Because what Proxima Centauri actually is, as a star, as a system, as an environment, is nothing like what you might expect. It is stranger, more dangerous, and more fascinating than almost anyone imagined before we started pointing our best telescopes at it. The star itself has a secret, and that secret completely changes the question of whether anything could ever survive there. If you are enjoying this journey, make sure to give this video a like. It really helps more curious minds like yours find these videos. Now let's talk about the star itself, because everything we've covered so far, the propulsion, the time dilation, the radiation, the psychology, all of that is about getting there, but what you're getting there to matters just as much. And Proxima Centauri, when you really look at it closely, is one of the most fascinating and deeply contradictory objects in the known galaxy. From Earth, it appears as a faint reddish smudge, so dim that you need a telescope to see it at all, even though it's the closest star to our Sun. That dimness is your first clue that this star is fundamentally different from the one we grew up under. Proxima Centauri is what astronomers call an M-type red dwarf. And red dwarfs are not just smaller, cooler versions of our Sun. They are an entirely different category of stellar object, with their own rules, their own rhythms, and their own particular brand of danger. In terms of sheer size, Proxima Centauri is humbling. It has roughly 1/8 the mass of our Sun, and about 1/7 its diameter. If our Sun were the size of a basketball, Proxima Centauri would be roughly the size of a golf ball. Its surface temperature sits at around 3000 Kelvin, compared to our Sun's 5778 Kelvin, which is why it glows red rather than yellow-white. It produces only about 1/500th of the total luminosity of our Sun. Standing on a hypothetical surface nearby, the star would appear larger in the sky than our Sun does from Earth, because the habitable zone around such a dim star sits much closer in, but the light would feel different, redder, softer in terms of visible wavelengths, but deceptive in its apparent gentleness, because Proxima Centauri is not gentle, not even close. Here is the secret the star has been keeping. Red dwarfs, and Proxima Centauri in particular, are among the most violently flare-active stars in the galaxy. A solar flare from our own Sun is already an extraordinary event. A powerful X-class flare from the Sun can disrupt radio communications, damage satellites, and send brilliant auroras dancing across the night sky. The most intense solar storm in recorded history, the Carrington event of 1859, was so powerful that telegraph wires sparked and caught fire across North America and Europe, and the auroras were visible as far south as Cuba and Hawaii. Now take that kind of energy and multiply it dramatically. In 2019, a team of astronomers using the Hubble Space Telescope, the Chandra X-ray Observatory, and several ground-based telescopes observed Proxima Centauri over an extended period as part of a campaign called the Proxima Campaign 2. What they found was deeply significant. Proxima regularly produces flares that, in terms of ultraviolet radiation, are up to 1,000 times more energetic in the ultraviolet wavelength specifically than the most powerful flares we see from our own Sun. One particular event observed during the campaign saw the star brighten by a factor of around 14,000 in just 10 seconds in the far ultraviolet range. 10 seconds, 14,000 times brighter. Then back to baseline, almost as fast. These aren't occasional events, these are routine. Proxima Centauri flares frequently, sometimes multiple times per day. and the planet Proxima Centauri b orbits so close to its star, completing a full orbit in just 11.2 days, that it sits right in the firing line of every single one of those blasts. This changes the habitability question profoundly. Even if Proxima b has liquid water, even if it has the right temperature range, even if it has the right atmospheric pressure, if it has no magnetic field, or a weak one, those ultraviolet and X-ray flares would be stripping away its atmosphere over geological timescales, sterilizing any surface with radiation, and bombarding whatever chemistry might exist there with levels of energy that very few complex molecules can survive. We don't yet know whether Proxima b has a magnetic field. That's one of the critical unknowns. Earth's magnetic field, generated by the churning of liquid iron in our planet's outer core, is what deflects the solar wind and protects our atmosphere from being gradually eroded away into space. Mars, which lost most of its global magnetic field billions of years ago, also lost most of its atmosphere as a result. Today, Mars is a thin-aired, radiation-bathed desert. The presence or absence of a magnetic field on Proxima b could be the single most important factor in whether that world is even remotely survivable. Some researchers have proposed that if Proxima b formed in a different location in the stellar system and migrated inward over time, it might have a more substantial iron core and a better chance of generating a protective field. Others have pointed out that tidal forces from the star, given how close the planet orbits, might have locked the planet's rotation so that one face always points toward Proxima Centauri and the other always faces away. This is called tidal locking, and it's the same reason we only ever see one face of our moon. A tidally locked planet would have a permanent day side and a permanent night side, a broiling hemisphere facing the star and a frozen one facing eternal darkness. That sounds extreme. But here's where it gets interesting. Some climate models suggest that a tidally locked planet with the right atmospheric density could actually develop persistent circulation patterns, essentially permanent weather systems that redistribute heat from the day side to the night side, and along the terminator, the ring-shaped twilight zone between the two hemispheres, conditions might actually be temperate. Liquid water might pool, temperatures might stabilize, life, if it were there at all, might cling to that thin strip of perpetual dawn. The universe loves edge cases. Now let's bring your ship into this picture. Because approaching Proxima Centauri is not like pulling into a calm harbor. It is like navigating toward a volatile, unpredictable fire that occasionally explodes with the energy of thousands of nuclear bombs simultaneously. Your ship, having crossed 4.24 light-years of interstellar space, now has to perform one of the most difficult maneuvers imaginable: deceleration. This is a problem that Breakthrough Starshot's tiny laser sail probes largely sidestep by being too small to carry deceleration systems and simply doing a flyby at 20% light speed, capturing data in a brief window. But a crewed ship or any probe that needs to actually enter orbit has to slow down. And slowing down from a meaningful fraction of light speed requires just as much energy as speeding up, which means you need twice the fuel or twice the engineering ingenuity compared to a one-way acceleration. Some proposed mission architectures suggest using the star's own magnetic field or stellar wind to brake, essentially an electromagnetic drag system. Others propose firing the engines in reverse over years. The math is brutal. Deceleration at 1 standard gravity, the same pull you feel standing on Earth, which happens to be a comfortable acceleration for human physiology, would take roughly a year to slow from 20% light speed. From higher fractions even longer, but let's say you manage it. Let's say your ship has slowed. You are now in the Proxima Centauri system. You are the first human beings to orbit another star. What do you actually see? The sky around you would look almost familiar, and yet fundamentally alien. The stars would be in nearly the same positions you'd see from Earth, because 4 light-years is a tiny step on the scale of the galaxy. But our own Sun, Sol, the star that warmed every human being who ever lived, would appear as a bright star in the constellation we'd call Cassiopeia from this vantage point. You could cover it with your fingertip. Everything humanity has ever built, loved, lost and dreamed would be tucked behind a single point of light no brighter than a dozen other stars in the sky, ahead of you, close now, filling your forward senses. Proxima Centauri glows with that characteristic red warmth. It's larger in apparent size than our Sun appears from Earth, but its light is deeply reddish, heavy in infrared wavelengths, thin in the blue and violet. Photosynthesis, as we know it on Earth, uses chlorophyll that's tuned to absorb red and blue light. In this system, red wavelengths dominate overwhelmingly, which has led some scientists to speculate that if plant-like life ever evolved on Proxima b, it might be black, absorbing all available wavelengths to extract every possible photon from that dim red glow, a world of black plants under a red sun. Strange doesn't begin to cover it, and then, as your sensors sweep the space around you, something else appears in the data. Because Proxima Centauri does not travel alone. The star is part of a triple star system, the Alpha Centauri system, though it orbits its 2 companions at an enormous distance. Alpha Centauri A and Alpha Centauri B are a binary pair, 2 stars locked in a gravitational embrace, roughly 4 trillion kilometers from each other, slowly circling their shared center of mass over an orbit that takes about 79.9 years. They're a beautiful pair. Alpha Centauri A is very similar to our own Sun in size, temperature and luminosity. Alpha Centauri B is slightly smaller and cooler. Together from Earth, they appear as the 3rd brightest star in the night sky, gleaming brilliantly from the southern constellation of Centaurus. Proxima Centauri sits much farther out from this pair, roughly 1.3 trillion kilometers away, which sounds vast, but is on stellar scales, close enough that the 3 are gravitationally bound. Whether Proxima is a permanent member of the system or a temporary gravitational companion that will eventually drift away is still a subject of some scientific debate. Some studies suggest it is truly bound, a long-term if distant 3rd partner. Others leave more room for uncertainty. From the Proxima Centauri system, Alpha Centauri A and B would appear as 2 extraordinarily brilliant stars in the sky, far brighter than any star appears from Earth, casting faint but real shadows on a night surface. Your ship, parked in orbit, would have 3 suns to contend with, though 2 of them are light weeks away and pose no real threat. What does pose a threat, and what your mission has been anticipating from the moment of launch, is the next flare. Your instruments are tracking Proxima Centauri's magnetic activity around the clock. When a major flare erupts, you have very little warning. Minutes at most. Your ship's shielding, heavy, layered, designed specifically for this environment, will absorb the blast, but a flare large enough and your crew will need to shelter in the most protected compartment of the vessel, a small room buried deep inside the ship, surrounded by water tanks and high-density polyethylene panels, waiting for the radiation storm to pass. This is not a hypothetical risk. It is a scheduled reality of life in this system. Research by astronomers at the University of Colorado Boulder and other institutions has modeled what Proxima b's surface would experience during major flare events. The ultraviolet flux at the surface, even assuming some atmospheric protection, would be lethal to unprotected life as we know it. The X-ray bombardment during peak flare events would strip electrons from atmospheric molecules, creating chemical reactions that could shred ozone layers within years. Life on Proxima b, if it ever existed, would have had billions of years to adapt to this environment, and red dwarfs live extraordinarily long lives. Proxima Centauri is estimated to be about 4.85 billion years old, just slightly older than our Sun. but because it burns its fuel so slowly and so efficiently, it has a predicted lifespan of about 4 trillion years. That roughly 300 times the current age of the universe, long after our sun has expanded into a red giant and incinerated the inner solar system. Long after the Milky Way has merged with Andromeda, Proxima Centauri will still be burning, quietly, redly, persistently. If life is patient enough, if evolution has billions upon billions of years to work, then perhaps the flares are not a death sentence. Perhaps they are simply a pressure, a filter, the kind of environmental challenge that over deep time selects for extraordinary resilience. Life on Earth, after all, has survived 5 mass extinctions, a planet-sterilizing bombardment in its early history, and a nearly complete global glaciation. Life is stubborn in ways that continually surprise us, and so you sit in orbit, scanning, measuring, sending data home at the speed of light, knowing it will take 4.24 years to arrive. Your instruments are mapping the planet below, looking for atmospheric signatures, hunting for the chemical fingerprints of biology, oxygen, methane, the specific combinations that Earth's own life has written into our atmosphere over billions of years. The James Webb Space Telescope gave us our first real tools for this kind of atmospheric spectroscopy at a distance. Your ship, this close, would be able to do it with extraordinary precision. And then, one day, a line appears in the data that makes someone stop breathing for a moment, a chemical signature that doesn't quite fit the models of a purely geological world. Something that needs a second look, and a third. No one says the word yet. It's too soon. The data needs to be checked, cross-referenced, verified. Science demands caution in proportion to the magnitude of the claim. But the room goes quiet in a way it hasn't since the launch. Is that what we think it might be? Let's be honest about something. The question underneath all of this, underneath the propulsion systems and the radiation shields and the time dilation math, has always been the same question. The one question that unites every culture, every civilization, every human being who has ever tilted their head back and stared up at the night sky. Are we alone? It is the oldest scientific question we've never answered, and everything we've built, launched, and imagined in the direction of Proxima Centauri, every telescope, every mission concept, every career dedicated to the search, is ultimately aimed at that one point, not just whether a planet exists there, not just whether water exists there, but whether something lives there, whether, across 4.24 light-years of cold interstellar silence, another story is being written. Let's talk about how we would actually know. The science of searching for life from a distance is called astrobiology, and it's one of the fastest-growing fields in modern science. For most of human history, looking for life on another world meant guessing, imagining canals on Mars, dreaming of jungle worlds beneath Venus's clouds. But over the last few decades, we've developed actual scientific tools for this, real methods, real signals to search for, and they all come back to one core concept: biosignatures. A biosignature is any measurable property of a planet, a gas, a chemical ratio, a physical structure, a pattern of light that is best explained by the presence of life rather than purely geological or chemical processes. The idea is elegant in its logic. Life doesn't just exist passively. Life changes things. It transforms its environment. It leaves a fingerprint. Earth is the perfect example. If an alien civilization pointed their telescope at our planet and analyzed the light passing through our atmosphere, they would see something extraordinary. They'd detect large amounts of oxygen, far more than could be maintained without a constant biological source, because oxygen is chemically reactive and bonds with other elements quickly. It would vanish from our atmosphere within a few million years if photosynthesis stopped replenishing it. They'd also detect methane, which is curious because oxygen and methane react with each other and destroy each other. The fact that both exist simultaneously is a powerful signal that something is actively producing both. That something on Earth is life, bacteria in wetlands and animal guts producing methane, plants and algae pumping out oxygen. That combination, oxygen and methane coexisting in an atmosphere, is one of the strongest biosignature pairs we know of. Finding it on another world wouldn't be absolute proof, but it would be an extraordinary, serious signal demanding immediate and intensive follow-up. Other biosignatures include nitrous oxide, also produced biologically on Earth, ozone, which forms from biologically produced oxygen, and specific ratios of carbon isotopes that living systems tend to favor. There's also the concept of a vegetation red edge, a sharp increase in reflectivity at specific infrared wavelengths that Earth's plant life produces, because chlorophyll reflects near-infrared light strongly. From space, our planet's continents glow with this signature wherever green vegetation covers the surface. A forested world around another star might show the same signal, or, as we discussed, something like it. Tuned to absorb the very different light of a red dwarf star, the James Webb Space Telescope, launched on Christmas Day, 2021, and now operating at the second Lagrange point, about 1.5 million kilometers from Earth, is the most powerful infrared telescope ever built, and one of its key scientific missions is exactly this: analyzing the atmospheres of exoplanets by observing them as they pass in front of their host stars. The starlight that filters through the planet's atmosphere carries the chemical fingerprints of whatever gases are present. Webb has already detected carbon dioxide in the atmosphere of a hot gas giant called WASP-39b and water vapor in several other systems. It's early work, but it's real. Proxima b is unfortunately difficult for Webb to observe in this way because it doesn't appear to transit its star from Earth's perspective, which is the geometry that makes atmospheric spectroscopy easiest. But a ship in the Proxima Centauri system would have no such limitation. Up close, with direct access to the planet and its star from multiple angles, the instruments aboard your vessel could perform spectroscopic analysis with a precision that no telescope back home could match. Every pass around the planet would add data. Every dawn and dusk on Proxima b, filtered through whatever atmosphere exists there, would be a page of chemistry waiting to be read. So your crew is reading, the instruments are running, and the data is building into something that starts to feel, cautiously, like a pattern. Here's what a genuine detection moment would look like. Not as a Hollywood event with alarms and celebrations, but as science actually works. Someone reviewing the spectral data notices an anomaly, a line in the absorption spectrum that corresponds to a specific molecule. They flag it. A second team member verifies the wavelength. They run the calibration checks. They check for instrumental error. They look for alternative explanations. Could this be produced by a known geological process? A volcanic emission? A photochemical reaction driven by the star's ultraviolet output? They model every non-biological explanation they can think of. Some of those explanations work for some molecules. Oxygen can, in theory, be produced abiotically by ultraviolet light-splitting water molecules in an atmosphere, with hydrogen escaping to space and oxygen accumulating. This is called a false positive, and it's something astrobiologists are acutely aware of. A detection has to survive every attempt to explain it away before anyone starts reaching for bigger conclusions. But let's say the data survives. Let's say the oxygen and methane signals are both present and strong. Let's say the vegetation edge equivalent shows up in the reflectance spectrum. Let's say the isotopic ratios in the carbon compounds match biological fractionation patterns rather than geological ones. One by one, the non-biological explanations fall away. What happens then? The first thing that happens is a message home, traveling at the speed of light, taking 4.24 years to arrive. Imagine being the person who writes that message, knowing that by the time anyone reads it, you'll be 4 years deeper into the mission, knowing that the response, the instructions, the reactions, the cascading decisions of every space agency and government and scientific institution on Earth will take another 4+ years to reach you. You are making history in real time, and you will not know how the world has received it for almost a decade. The message would be scientific first, careful, hedged in the language of probability and confidence intervals. We have detected spectral signatures consistent with biological processes. Confidence level high, alternative explanations systematically excluded, requesting peer review of attached data package. Something like that. Precise. Measured. But somewhere in that message, maybe in a personal log, maybe in a line between the technical summaries, someone would find the words for what it actually means. And those words would reach Earth and shatter something. Not in a bad way. In the way that all true discoveries shatter things, by replacing a world that seemed complete with a universe that is suddenly, overwhelmingly larger. We are not alone. Think about what that would do to the human species. Not the panic of science fiction, not the invasion narrative, not the fear, the real psychological, philosophical, and spiritual impact of genuine confirmed evidence that life exists beyond Earth. Every religious tradition that has ever grappled with the uniqueness of humanity would need to grapple again with something new. Every philosophical framework built around the centrality of human consciousness would need to expand. Every assumption we carry about what life is, what it means to be alive, what the universe is for, all of it would shift, not violently, but permanently and profoundly, in the way that all great scientific revelations shift us. We went through something like this before, though smaller, when Copernicus and Galileo demonstrated that Earth was not the center of the universe, that we orbited the Sun and not the other way around. It was deeply unsettling to many people. It felt like a demotion, like being told the stage you thought was the whole theater is actually just a seat in the back of an auditorium. And yet, and this is what always strikes me, humanity adapted. We integrated that knowledge. We found new meaning in it. And most people today feel not diminished but enlarged by the knowledge that we live on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies. The discovery of life beyond Earth would do that again. Bigger, faster, and with something the Copernican revolution didn't offer, the possibility of connection, of comparison, of asking what life looks like when it evolves under a red sun on a tidally locked world with constant ultraviolet bombardment and a surface chemistry we're only beginning to understand. And here's the thing, it wouldn't even need to be intelligent life to matter. A single microbial ecosystem on Proxima b would be the second independent origin of life in the history of the known universe. And if it happened twice, here and there, in the same stellar neighborhood, then the mathematics of probability demand that it has happened billions of times across the galaxy. Life would not be a miracle, it would be a law, a consequence of chemistry, given time and the right conditions. But what if we find nothing? What if the spectral data comes back clean? What if every biosignature search returns negative? What if Proxima b is a bare, radiation-scoured rock with a thin atmosphere of carbon dioxide and not a whisper of biology anywhere in the data? This too would be an answer, and in some ways, a more haunting one. Because here is the thing about silence. The universe is vast. The number of stars is staggering, somewhere around 200 billion in our galaxy alone, and roughly 2 trillion galaxies visible in the observable universe. We now know that planets are extraordinarily common. NASA's Kepler Space Telescope confirmed that most stars host planets, and that rocky, potentially habitable worlds are abundant across the galaxy. Given those numbers, given the age of the universe at 13.8 billion years, given the sheer number of opportunities for chemistry to self-organize into living systems. Why do we not hear anything? This is the Fermi paradox, named for physicist Enrico Fermi, who, during a casual lunch conversation in 1950, reportedly asked a simple, devastating question: where is everybody? If intelligent life is common, and the galaxy is old enough that many civilizations should have had time to spread across it, why is space so quiet? Why have we detected no signals? Why have we found no artifacts, no megastructures, no evidence of engineering on a cosmic scale? There are many proposed answers, some optimistic. Perhaps interstellar travel is simply so difficult that even advanced civilizations don't do it. Perhaps signals are there, but we're not looking in the right way. Perhaps the universe is full of life at the microbial level, but complex technological intelligence is extraordinarily rare. Perhaps the timescales involved mean that civilizations rise and fall without overlapping. Some answers are darker. The Great Filter hypothesis suggests that somewhere along the path from simple chemistry to spacefaring civilization, there is a step that almost nothing survives, a filter, and the terrifying question is whether that filter lies behind us or ahead of us. If simple life is rare, if the jump from chemistry to biology is the hard part, then we might have already passed through it and the future is open. But if simple life is common and complex life is rare, then the filter might lie somewhere further along the path, in the transition to multicellular life, or to intelligence, or to a civilization that survives its own technology. And if that's true, then our silence in the cosmos might be a warning, not a comfort. Finding even simple microbial life on Proxima b, the nearest star, would suggest that life arises easily wherever conditions allow, which would make the Great Filter's location much more ominous. Because the galaxy should then be full of life that never made it past some later, lethal threshold. The universe is not always reassuring, but it is always honest, and every answer it gives us, positive or negative, moves us closer to understanding what we actually are. Your crew is still reading the data. The argument in the analysis room has been going for hours now. One team member is convinced the methane signature is geological, a hydrothermal source consistent with volcanic activity. Another is equally convinced the isotopic ratios rule that out. A third is running the models again for the fourth time, checking for instrument drift. Someone has made coffee that no one has touched. The red light of Proxima Centauri hangs in the viewport, patient and ancient and completely indifferent to the drama unfolding in the ship floating before it. This is science, not the triumphant announcement, the arguing, the checking. The humility of people who know that wanting something to be true is not the same as it being true, and the courage of people who, despite all that caution, are willing to follow the evidence wherever it leads. And wherever it leads, toward life or toward silence, the next phase of the mission begins the same way, with descent, with the decision to get closer, to send something down into that atmosphere, through those clouds, toward whatever surface waits below. And that decision brings its own cascade of questions, its own engineering nightmares, its own breathtaking moments. Because landing on Proxima b, or even sending a probe through its atmosphere, is one of the most complex and dangerous things any mission could attempt. What happens when you try? What does the surface look like? And what would it feel like, physically in your body, in your bones, to stand on the ground of another world orbiting another star? That's where we're going right now. And I promise you, it is stranger and more beautiful than anything we've covered so far. Stay with me. There is a moment in every great journey where the abstract becomes real, where the numbers on a screen become wind on your face, where the mission briefing becomes the ground rushing up to meet you, where everything you planned for, trained for, and sacrificed for collapses into a single, irreversible act For your crew orbiting Proxima Centauri after a crossing that took years and reshaped everyone aboard in ways both measurable and immeasurable, that moment is now. The decision has been made. A probe is going down, and depending on what it finds, you might be going down after it. Let's talk about what that actually involves. Because descending into the atmosphere of an alien world is not like landing a plane. It is not even much like landing the Apollo modules on the moon. It is a controlled fall into the unknown, governed by physics you've modeled, and atmospheres you've estimated, and surface conditions you've inferred from data gathered millions of kilometers away. Every assumption you made during the years of planning is about to be tested against reality, and reality, as any scientist will tell you, has a habit of being more complicated than the model. The first challenge is the atmosphere itself. We don't yet know, and won't know until we get there, exactly what Proxima B's atmosphere looks like, if it has one at all. The possibilities span an enormous range, shaped by factors we're still working to understand from Earth. On one end of the spectrum, Proxima B might have lost most of its atmosphere long ago. The intense stellar wind from Proxima Centauri, the constant outflow of charged particles from the star, is far more powerful relative to the planet's orbit than what Earth experiences from our Sun. Without a strong magnetic field to deflect it, that wind would gradually erode the upper atmosphere over billions of years, much the way Mars lost its own. A thin, unbreathable remnant might be all that remains, a world like a slightly warmer version of Mars, where the atmospheric pressure at the surface is so low that liquid water boils away instantly, and no amount of sunscreen protects you from the radiation. On the other end, if Proxima B formed with enough volatile material and has maintained geological activity, volcanism replenishing gases lost to space, it might have a dense, complex atmosphere, perhaps rich in carbon dioxide, like Venus and the early Earth, perhaps with nitrogen and trace gases in proportions we haven't encountered before, perhaps, in the most exciting scenario, with water vapor and oxygen and the unmistakable chemistry of a living world. The probe you send down is designed to survive all of these possibilities. It's built like a layered onion, an aeroshell on the outside to handle the heat of atmospheric entry, instruments nested inside measuring pressure, temperature, chemical composition, wind speed, and radiation at every altitude. As it descends, it transmits in real time. Every second of data is precious because probes fail, heat shields crack, parachutes malfunction. You take nothing for granted. Entry interface, the point where the probe hits atmosphere dense enough to begin decelerating, happens at a speed that turns the air ahead of it into plasma. The aeroshell glows white-hot, shedding energy in a cocoon of superheated gas. Communications black out for several minutes as the plasma sheath blocks radio signals. This is the period mission controllers call the 7 minutes of terror, borrowed from the language used to describe the entry of NASA's Curiosity rover at Mars, which had to perform a fully autonomous, enormously complex sequence of events because the signal delay made real-time control impossible. At Proxima Centauri, the signal delay is measured not in minutes, but in years. Everything the probe does from the moment of release is autonomous. It was programmed before launch with every contingency the engineers could imagine, and now it is alone, falling, making decisions at the speed of its onboard computer, with no one able to reach in and help. The plasma phase ends. Atmospheric pressure builds. A drogue chute deploys, then the main canopy, slowing the descent to something survivable. The probe's instruments wake up, and data begins to flow. What does it find? Let's build the most scientifically plausible picture we can, based on everything we currently know and the models our best researchers have constructed. The atmosphere, our instruments suggest, is thinner than Earth's but not absent. Carbon dioxide and nitrogen dominate, with traces of other gases, some intriguing, some ambiguous. Pressure at the surface, the probe's sensors read, is somewhere around half of what you'd experience standing at sea level on Earth. Enough to be physically meaningful, not enough to breathe without assistance. Temperature on the day side, the hemisphere permanently facing Proxima Centauri, is warm. Warmer than comfortable, but not Venus-like. The star's dim red light deposits energy slowly but steadily, and without the dynamic weather systems that Earth's rotating atmosphere creates, the day side accumulates heat. Your probe is descending near the terminator, that ribbon of perpetual twilight between the burning face and the frozen one, where models predict the most moderate conditions. The light here is extraordinary. Proxima Centauri hangs low on the horizon, huge and deeply red, like a sunset that never ends and never quite becomes dark. The sky is not the blue of Earth's sky. There is not enough Rayleigh scattering of the right wavelengths to produce that effect. Instead, the sky might be a deep violet or reddish purple hue, depending on atmospheric composition, with the star casting long, reddish shadows across a landscape that has never, in all its billions of years, experienced a day or night in any way we would recognize. The surface comes into view through the probe's cameras, and this is the part that will make the scientists back on the ship go completely silent. It is not a barren, grey wasteland. It is not a smooth, featureless plain. It is geological, textured, ancient. There are craters, evidence of impact history spanning billions of years. There are what appear to be dried channels, winding structures that look unmistakably like the remnants of flowing liquid, carved long ago, or perhaps recently, by water or some other fluid, working its way across the surface under conditions now changed. There are what might be cliffs of layered rock, the strata recording geological epochs in compressed silence. And in the low-lying areas near the terminator, where temperatures sit in a range that water could theoretically remain liquid, there is something dark, something that catches the light differently from the surrounding rock, something that, to a geologist's trained eye, looks almost like, but might not be, moisture. The probe sets down. Its legs compress against an uneven surface. It's stable, all systems nominal, and its chemical analysis arm extends toward the ground. Let's pause here and feel the weight of this moment, because that probe, that small autonomous machine built by human hands on a planet 4.24 light-years away, is about to touch the soil of another world orbiting another star. It is the furthest any human-made object has ever landed. Every gram of it was carried across interstellar space. Every component was designed by engineers who spent their careers on this single goal. And the data it now sends back will be the first direct chemical measurement ever taken of material from another stellar system. The signal travels back to your ship in orbit at the speed of light, a journey of mere seconds at this scale. It arrives, it is decoded, and the analysis begins. The soil sample is mineral-rich, silicates, iron compounds, traces of sulfur. The chemistry is recognizably planetary, not alien in any exotic sense. This is reassuring and also grounding. The universe, it turns out, is built from the same periodic table everywhere. The same atoms that make up Earth's crust make up this crust. Carbon, oxygen, silicon, iron. The universe has one ingredient list. It just uses it differently in different places. But then, in the spectral analysis of the soil chemistry, in the breakdown of organic compounds at the surface, there are carbon-bearing molecules, complex ones, not necessarily biological, but not obviously abiotic either. The kind of chemistry that sits on the knife edge between geology and biology and refuses to declare itself definitively on either side. It is tantalizing in the most scientifically legitimate sense of that word. It demands more data. It demands a closer look. This is the moment someone in the crew says, "We need to go down ourselves." And that conversation, the decision about whether to attempt a crude descent, is one of the most profound that human beings have ever had to make. Because this is not a simulation. There is no abort protocol that gets you home in an afternoon. If the descent vehicle has a problem in the lower atmosphere, if the landing site is softer than the radar suggested, if a flare erupts from the star during the descent window and floods the entry corridor with radiation, the options for rescue are extraordinarily limited. But this is also why you came. Not just to orbit, not just to send robots, to be there, to stand on the surface, to look up with human eyes at a red star in an alien sky and say, "We made it here, we, the curious ones, the ones who could not stop asking what was out there. We came all this way and we are standing on it. The crew vote is unanimous. They're going. Preparation for the crewed descent takes weeks. Every system on the landing vehicle is checked and checked again. The entry trajectory is modeled hundreds of times, refined with data from the probe's atmospheric readings. The landing site is selected, a flat area near the terminator within a few kilometers of the zone where that dark moisture-suggestive material was detected. Suits are inspected. Contingency plans are rehearsed until they are reflexive. The crew members making the descent have been preparing for this moment for most of their adult lives. They were selected partly for their technical skills, partly for their psychological resilience, partly, and the mission planners were honest about this, for their ability to handle the existential weight of being first, of knowing that whatever happens next has never happened before, that there is no manual for this specific experience, that they are, in the deepest sense, beyond the edge of the map. The landing vehicle detaches from the orbiting ship, thrusters fire, the descent begins in the orbiting ship. The crew members who remain watch on screens as the vehicle shrinks to a point and then vanishes into the upper reaches of Proxima B's atmosphere. Communication is maintained, a thin thread of radio signal connecting the two halves of the mission across an increasingly terrifying gap. Entry interface, plasma blackout, 2 minutes of silence that feel like geological epochs. Then the signal returns, the parachute has deployed, the landing vehicle is descending under canopy, altitude dropping, velocity dropping, retro rockets firing in the final seconds contact. One word comes back over the radio, just that. But the voice carrying it is shaking in a way that the speaker clearly wasn't expecting, and everyone who hears it, in the orbiting ship, and eventually 4.24 years later on Earth, will know exactly what it cost to say it with any composure at all. The hatch opens, the ramp extends, and the first human being to set foot on the surface of a world orbiting another star takes one step, then another, onto the ancient red-lit ground of Proxima b. What does it feel like physically? The gravity here is estimated to be slightly different from Earth's. Proxima b's mass is uncertain, but it is likely close enough to Earth mass that gravity at the surface would be broadly comparable. Your legs work. Your sense of balance holds. The suit is pressurized, familiar from thousands of hours of training, but the view through the helmet visor is nothing like any training environment ever prepared you for. The ground is dark reddish-grey, littered with small rocks worn smooth by processes you don't yet understand. Wind moves, slowly but perceptibly, carrying fine dust that settles on the suit's exterior. The air outside, you cannot breathe it, but you can hear it moving against the suit, a faint whisper of another world's breath. Proxima Centauri sits near the horizon, filling a larger patch of sky than our sun, bathing everything in that extraordinary, ancient red light that has shone on this surface for nearly 5 billion years without once being witnessed by a conscious mind. Until now, you look down at your boots, at the undisturbed surface around them, undisturbed for billions of years, for the entire history of this world, until this moment, and you think about everyone who got you here, every engineer, every scientist, every person who looked at the stars and refused to look away, every generation that built toward this without knowing it, from the first human who noticed that the lights in the sky moved with patterns, to the person who ground the first telescope lens, to the team that designed the engine that carried you across the gap between stars. You are the product of an unbroken chain of curiosity stretching back to the first conscious creature that looked up and wondered, and you are here, actually here, standing on another world. But the mission is not done, because standing on the surface is only the beginning of what this place has to tell you. The instruments are running, the samples are being collected, and just a few kilometers away, visible now as a darker patch against the pale regolith, catching the red light at a slightly different angle, is the area that the probe flagged. The place where the chemistry got interesting. Whatever is there, water, or the remnant of it, or something stranger, it is waiting. And you have limited time before the next radiation event, before the landing window closes, before the chain of decisions made back home years ago forces you to the next phase of the mission. What do you find when you get there? What does the analysis reveal? And what does the answer, whatever it turns out to be, mean for the question you've been carrying since the beginning? That is where the next part takes us, to the edge of the dark patch, to the moment the instrument readings stop being ambiguous, to the answer that changes everything, or the silence that changes it differently. The ground crunches softly under your boots as you start walking. You are walking on another world. Let that settle for a moment before we move forward. Not in a simulation, not in a dream, on the actual surface of a planet orbiting a star that is not our sun, in a system that took everything humanity had to reach. Every step you take is the first step ever taken in that spot. Every boot print you leave in the reddish dust is the first mark any conscious being has ever made on this ancient ground, and you are walking towards something. The dark patch is about 3 kilometers from the landing site. On Earth, 3 kilometers is a casual walk, 20 minutes at a comfortable pace. Here you move more carefully. The terrain is uneven in ways the orbital surveys couldn't fully capture. Rocks that looked like small pebbles from above turn out to be ankle-height obstacles, worn and rounded in ways that strongly suggest, the action of flowing liquid at some point in this world's history. Your geologist's eye catches things as you walk. Layered outcroppings in a nearby cliff face, each band of rock a different era of this planet's story, compressed into stone and waiting to be read like a book in a language no one has ever translated. The wind picks up briefly. Fine dust, lighter than earth dust, different in composition, swirls around your boots and then settles. The sky above you is that deep, unsettling violet red, and Proxima Centauri hangs low and enormous, painting every surface in warm crimson tones that make the landscape feel simultaneously beautiful and wrong in a way your brain cannot quite categorize. Beautiful because light is beautiful, wrong because every instinct built into you over millions of years of primate evolution is quietly insisting that this is not right. That skies are blue, that sunlight is yellow, that home is somewhere behind you, a point of light you cannot even distinguish from the other stars at this time of day. You keep walking. At around 2 kilometers out, the instruments on your suit begin registering something, a change in the atmospheric readings close to the surface. Humidity, if that word even applies to this atmosphere, is slightly elevated compared to baseline. The temperature here is marginally lower than the surrounding terrain, which is consistent with evaporative cooling. Something is releasing moisture into the air. Your pulse increases. You don't announce it over the radio yet. You keep walking. Science demands data before declarations. At 2.5 kilometers, the ground changes texture underfoot. The coarse, rocky regolith gives way to something finer, darker. The rock here is a different color, almost black in patches, compared to the reddish-gray of the surrounding terrain. And the surface has a quality to it that makes you slow down and look very carefully before taking each step. It has a slight give, not much, not like mud, But not like the rigid, dry rock you've been crossing for the last hour either. You crouch down. The suit's external sampling arm extends. You activate the close-range chemical analyzer and point it at the dark surface in front of you. The readout begins scrolling water. Not vapor, not hydrated minerals with water molecules locked into their crystal structure, though those are present too. Liquid water, a thin film of it, barely a millimeter deep in places, pooling in the microscopic depressions of the rock surface. Liquid water on the surface of a planet orbiting Proxima Centauri, sitting quietly in the eternal twilight of the Terminator zone, where the temperature is just barely narrowly, continuously above the freezing point. You say it out loud before you mean to, just the two words. Into the radio, quietly, almost reverently. There's water. The silence on the other end of the radio lasts exactly 4 seconds. Then everyone starts talking at once. Water on Proxima b is not by itself proof of anything biological. Water is extraordinarily common in the universe. It forms readily from hydrogen and oxygen, the first and third most abundant elements in the cosmos. Comets carry it. Asteroids carry it. The moons of Jupiter and Saturn have vast oceans of it locked beneath their icy surfaces. Mars almost certainly had it once in enormous quantities. Water is a necessary condition for life as we understand it, but it is not a sufficient one. It is the stage, not the play, but it is the stage. And finding that the stage exists right here at the terminator of Proxima b, in the exact zone that models predicted might be temperate enough to support it, is a confirmation that sends the mission's scientific credibility skyrocketing. The models were right. The planet is not a dead, desiccated rock. It has liquid water. It has the most fundamental ingredient. You stand up. You look at the dark, wet ground stretching ahead of you. The liquid film catches the light of Proxima Centauri and throws it back in deep red glints, like a scattered mosaic of tiny rubies laid across the ancient stone. It is, against all rational expectation, one of the most beautiful things you have ever seen. You take a sample. You take several samples. You label each one meticulously with location data, timestamp, atmospheric conditions, and a note in your log that will eventually travel 4.24 light years and be read by people who are currently, right now, going about their ordinary lives on Earth with no idea that this moment is happening. Back on the ship that evening, your crew uses the word evening loosely as a psychological anchor because there is no actual evening on a tidally locked world. The samples go into the analysis lab. The work that follows is painstaking, slow, and subject to a level of procedural rigor that makes ordinary laboratory science look casual. Because the stakes of a false positive here are immense, announcing biological contamination when there is none, or, worse, detecting Earth contamination from the ship itself masquerading as native biology would be a catastrophe for the mission and for science. Every instrument is verified. Contamination protocols are triple-checked. Blank samples from the ship's own sterile storage are run through the same pipeline so their results can be subtracted from the data. The team works in shifts, with fresh eyes reviewing every result, and with a standing rule that no one person's excitement gets to outrun the group's collective rigor. The water itself, under analysis, is extraordinary in its chemistry. It is not pure, but then water on Earth is never pure either. It contains dissolved minerals consistent with the rock it's been flowing over and through. It contains sulfate compounds, iron ions, traces of chlorine-bearing molecules. The pH is slightly acidic, not dramatically different from some acidic water environments on Earth, volcanic lakes. Certain deep-sea hydrothermal systems where life nevertheless thrives, and then, buried in the organic chemistry panel, in the breakdown of carbon-containing molecules extracted from the water sample, something appears that stops the lead astrobiologist mid-sentence. Amino acids, not all of them, not a complete set, but 2 of them, clearly present above background noise levels. Glycine and alanine, the two simplest amino acids, the same ones found in meteorites that have landed on Earth, the same ones produced in classic laboratory simulations of early Earth chemistry like the Miller-Urey experiment of 1952. Their presence does not require life. Amino acids can and do form through abiotic chemistry. We know this, the team knows this, but here is what makes the team go very, very quiet. Both of these amino acids in this sample show a strong preference for left-handedness. Let me explain why that matters. Amino acids come in two mirror image forms, left-handed and right-handed, like a pair of gloves. Chemically, they are identical in almost every property. But life, at least all life on Earth, uses exclusively left-handed amino acids. Every protein in your body, every enzyme in every living cell on this planet is built from left-handed amino acids and right-handed sugars. This is called homochirality, and it is one of the most distinctive fingerprints of biology. Abiotic chemistry, by contrast, the random chemistry of space and rocks and ultraviolet light, typically produces amino acids in roughly equal mixtures of left and right-handed forms. A 50-50 racemic mixture is the signature of non-biological production. The sample from Proxima b is not 50-50. It is heavily left-handed, the number the instrument returns. The enantiomeric excess, the measure of how far the ratio deviates from 50-50, is significant, high enough that the probability of it arising from purely random abiotic chemistry is very low, not impossible, but very low. The room is silent for a long time after that result is confirmed. Someone eventually says, "We need to go back and get more samples." Everyone nods. That is the correct response. More data, more locations, more verification, more attempts to find an alternative explanation. This is how science is supposed to work, and everyone in that room is a scientist first and a human being second, at least in this moment. But the human being part is still there, and later, in personal logs, in quiet conversations during off-shift hours, in the careful way people avoid saying the word out loud, as if saying it might jinx the analysis, everyone is thinking the same thing. This might be it. This might actually be it. Over the following weeks, your crew makes 3 more surface excursions, sampling at different locations along the Terminator, sampling from the shallow water pools at different depths, collecting rock cores from the layered cliff face that preserves billions of years of geological history in compressed stone. Each sample goes through the same rigorous analysis pipeline. Each set of results is reviewed by the full team. The picture that emerges is not clean. Science rarely gives you clean. It gives you a pattern with noise, a signal with uncertainty, a story that is probably true but has chapters that still need filling in. What the pattern shows is this. The amino acid homochirality signal is present in multiple samples from different locations. It is strongest in the samples taken from the areas with the most persistent liquid water, the deepest pools, the most sheltered depressions, the places where conditions are most stable. It is weaker or absent in drier, more exposed areas where radiation exposure is higher. This is consistent with what you'd expect from biology, concentrated where conditions are most favorable, absent where they're harshest. There are also complex organic polymers in the water samples, long-chain carbon molecules that on Earth would immediately suggest biological origin. Here, the team is more cautious. Complex organics can also form from Fischer-Tropsch-type reactions, from ultraviolet processing of simpler molecules over long timescales. But the specific structures, the specific chain lengths, the specific functional groups attached, they are not what abiotic chemistry typically produces. And finally, in one sample, taken from a thin biofilm-like layer coating the underside of a rock at the edge of the deepest water pool, there are what appear to be microscopic structures, not crystals, not mineral formations, shapes, rounded, bounded shapes with internal organization, visible under the highest resolution of the ship's electron microscope. They are not definitive. They are not clearly labeled, "I am a cell." They are ambiguous in the careful, infuriating, magnificent way that real discoveries always are. But they are there. And they are unlike any mineral structure in the geological literature. The message home is composed over 3 days. Every word is debated, every claim is hedged to precisely the degree the evidence warrants, no more, no less. It is a masterpiece of scientific restraint, which means it is also, between every line, absolutely electric, with the thing it is trying not to say too loudly. The conclusion, stated carefully, is this: we have identified multiple independent lines of evidence consistent with biological or pre-biological chemistry in the terminator zone of Proxima Centauri b. No definitive conclusion is yet possible. Further analysis is required. We recommend extended mission duration and request peer review of attached full data package. We believe these findings warrant the highest priority in future mission planning. It is sent, at the speed of light, into the dark, toward a small yellow star 4.24 light-years away, where billions of people are right now sleeping, working, loving, arguing, eating breakfast, watching videos, having conversations about things that feel urgent and important, and that are all, every single one of them, about to become simultaneously more and less significant than they were before. In 4.24 years, that message will arrive. Someone will decode it. Someone will read those carefully hedged conclusions. Someone will look at the attached data and sit very still for a very long time. And then the world will begin, slowly, unstoppably, to change. But you are still here. The mission is not over. The data is still accumulating. The planet below is still turning its slow, eternal face toward its ancient star. And the question that brought you here, the question humanity has been carrying since before we had science, before we had telescopes, before we had language sophisticated enough to ask it properly, has not been fully answered, not yet, because what you've found is chemistry, extraordinary, suggestive, deeply exciting chemistry. But chemistry is not life. Life is not just molecules arranged in interesting ways. Life is process. Life is replication, metabolism, response to environment, the transfer of information from one generation to the next. Chemistry is the alphabet. Life is the sentence. And you have not yet heard the sentence. To hear it, you would need to go deeper, to take the samples back to a fully equipped laboratory on Earth, where the best analytical tools in human history could be brought to bear, to run experiments that take months, not hours, to sequence whatever passes for genetic material here, if anything does, and compare it to the architecture of life on Earth. That comparison would be the most important experiment in the history of science. Because if the life on Proxima b, if it is life, shares any fundamental architecture with life on Earth, it would suggest either a common origin or a universal logic to biology. That life, wherever it arises, converges on the same solutions, the same molecular toolkit, the same basic machinery, which would mean the universe has a preferred way of being alive. But if the life on Proxima b is completely different, a second, independent invention of biology, using different molecules, different structures, a different code, then we would know something even more profound. That life is not one trick the universe learned once and repeated. It is something the universe does wherever it can, an emergent property of chemistry and time and energy. As natural as gravity, as inevitable as entropy, either answer reshapes everything. The ship is preparing to begin the long process of deceleration toward departure trajectory. The samples are secured. The data is backed up across multiple redundant systems. The crew is running final surface checks, final instrument calibrations, final farewells to a surface they will never stand on again. Someone goes outside one last time. Not for science, just to stand there, to look at the sky and the rock and the thin shimmer of water in the low places, to commit it to memory in a way that no recording can replicate, to feel the alien wind, thin, cold at the Terminator's edge, moving against the suit one final time. They stand there for 11 minutes. No one on the radio asks them to hurry, and then they come inside. The hatch seals. The landing vehicle lifts off. The surface of Proxima B falls away beneath you, and the red star grows smaller in the rear cameras, and the long journey home begins. You are carrying something back with you that the universe held in secret for 5 billion years, whether it is proof of life, or the chemistry that was almost life, or the conditions that will eventually become life. You are carrying it home, across the dark, back to the people who sent you here with all their hope and all their curiosity and all their faith that asking hard questions is worth whatever it costs. The hardest part of any journey is not always the destination. Sometimes it's the return, the long way back, the slow re-entry into a life that kept moving while you were gone, into a world that changed without asking your permission, into a version of yourself that no longer quite fits the person you were when you left. Your ship is pointed home. The engines are burning at the steady, patient thrust that will build your velocity over weeks and months until you are once again moving at a meaningful fraction of the speed of light, this time in the direction of a small yellow star that looks, from here, like any other star, unremarkable, quiet, but yours. The journey home will take roughly as long as the journey out. The physics doesn't care about your emotional state. The distance is the same in both directions, and so the crew settles back into the rhythms of deep space life, the watch rotations, the maintenance cycles, the experiments still running in the science module, the careful tending of the food systems, the measured social rituals that keep a small group of people sane and functioning in an enclosed space for years on end. But something is different now. Something fundamental has shifted in the psychological atmosphere of the ship in ways that the mission planners anticipated only partially, and that no training program could have fully prepared anyone for. You have been somewhere, you have done something that no human being has ever done, and now you have to live with that. In close quarters, for years, before you can share it with anyone outside this ship. Psychologists who study extreme environments, Antarctic expeditions, submarine deployments, long-duration space missions, have identified a phenomenon they call the third quarter effect. In missions with a defined duration, morale and cohesion tend to decline most sharply not at the beginning, when everything is new and purposeful, and not at the end, when the finish line is close enough to generate excitement. The hardest stretch is the third quarter, the point where the novelty has worn off completely, the end is not yet close enough to feel real, and the accumulated weight of isolation, confinement, and distance from home is at its heaviest. On the return crossing from Proxima Centauri, the third quarter is not just a psychological phase, it is years of time. Real, unmerciful, tick-by-tick years of being suspended between a world you have left and a world you are returning to, neither fully present in either place, carrying a secret too large for casual conversation and too important to process alone. The crew members handle this differently. Some throw themselves into work, processing data, writing detailed mission reports, conducting secondary experiments, filling every available hour with purposeful activity. Some go inward, journaling obsessively, reading, spending long hours in the observation module, watching the stars in a sky that never changes and finding, somehow, that this is comforting. Some talk, a lot, about everything and nothing, in the way that humans do when language is the last available tether to normalcy, and some, inevitably, struggle. Not catastrophically, the selection process was rigorous, and the psychological support systems on the ship are better than anything that existed on earlier long-duration missions. But the human mind, under sustained extraordinary pressure, does not always behave predictably. Relationships that were solid under training conditions develop friction under the grinding weight of years. Small irritations compound. The gap between who you are and who you need to be for the mission can widen in ways that take real effort to close. What carries people through, what that research consistently shows matters most in extreme isolation, is meaning, the sense that what you are doing matters, that the difficulty is worth it, that you are part of something larger than your own comfort or discomfort, and this crew has that in abundance. Whatever else is uncertain, whatever the final scientific verdict on those samples turns out to be, they know what they found. They were there, they stood on the surface, they felt the alien wind, they saw the water glinting in the red light, they sent the message home. No amount of third-quarter difficulty can take that away from them, and on the hardest days, when the walls feel closer than usual and the years feel longer than usual, that knowledge is the thing people reach for, the anchor that holds when everything else is drifting. There is another dimension to the return journey that is worth sitting with, one that doesn't get talked about enough in the technical literature, but that anyone who thinks carefully about this mission will eventually arrive at. The people waiting for you on Earth are not the same people who said goodbye. Time dilation, at the speeds your ship is traveling, means the difference between ship time and Earth time is real but not dramatic, perhaps a few months over the full round trip. So you haven't been gone for a century while experiencing only decades. The gap is smaller than the most extreme relativistic scenarios, but it is still real, and it adds to the more ordinary displacement caused simply by the passage of time. Everyone you left behind has aged. Parents who were healthy when you departed may now be elderly or gone. Children you left as young adults are now in the middle of their lives. Friends have made decisions, had experiences, built new relationships that have nothing to do with you. The world has had elections, discoveries, disasters, and transformations. Music has changed, cities have changed, technology has changed. You know this abstractly when you leave, but knowing something abstractly and experiencing it are separated by an enormous emotional distance. The astronauts who returned from the relatively short Apollo missions, gone for only about 2 weeks, reported that the psychological reintegration was harder than expected. The experience of having been somewhere so remote, so unlike anything in ordinary life, created a kind of distance between them and the people they'd left behind. Not a hostile distance, not an unbridgeable one, but real. A sense of carrying something that couldn't be fully shared, a chapter of experience that existed only inside the people who had lived it. Now multiply that by years, by the scale of interstellar space, by the fact that you didn't just go somewhere remote, you went to another star. You found what might be evidence of life. You were changed at some fundamental level by the experience of standing on ground that belonged to no human tradition, no human history, no human story until you arrived and made it one. Coming home from that is its own journey, and it begins before the ship lands. The communications from Earth, arriving in batches due to transmission scheduling, give you glimpses of what you're returning to. The scientific community's response to your data, received 4+ years after you sent it, has been, as expected, a mixture of intense excitement and methodical skepticism. Multiple independent research groups have been working to verify your findings from Earth's end using the most powerful telescopes and spectroscopic instruments available to look for corroborating signals from Proxima B. Some have found hints consistent with your data, others have found nothing conclusive. The debate is vigorous exactly as it should be. The broader public response, filtered through news summaries in the communications packages, is harder to characterize. There is excitement, enormous excitement, in many places. There are viral moments, cultural eruptions, a global conversation about what your findings mean for humanity's understanding of its place in the universe. There are also, predictably, voices of skepticism and denial. People who doubt the mission, doubt the data, doubt the conclusions. There are philosophical and religious commentaries spanning every possible position. There are political arguments about what to do next, who owns the discovery, what obligations humanity has toward a potentially living world it has now visited. This is the world you are returning to. Not a world that has received your findings with uniform awe and immediately unified around their implications. The real world, the complicated one, the one that processes even the most extraordinary events through all its existing filters of belief, interest, fear, and hope. You find, reading these communications, that you feel something unexpected, not disappointment at the complexity of the response, something closer to love, a fierce, aching tenderness for a species that can simultaneously be this petty and this magnificent, that can argue about everything and also build a ship and send it across the light years and stand on the surface of another world and send back data with trembling hands. As the ship draws closer to home, still years out, but now with the sun brightening slowly in the forward cameras from a star among stars into something noticeably distinct, the crew begins to undergo what the mission psychologists called re-entry preparation. Not the physical re-entry into Earth's atmosphere, which is still far in the future, but the psychological re-entry into ordinary human life. This involves structured conversations about expectations, about the gap between the experience you've had and the experience others will project onto you, about the fact that you will be, for the rest of your lives, people who did this, and that identity, as extraordinary as it is, can be both a gift and a burden. You will be asked to speak about it endlessly, to represent it, to carry the weight of meaning that other people attach to it. At the same time, you will need to find ways to be ordinary people again, to grocery shop, to have arguments about nothing important, to fall asleep watching something forgettable, to exist in the smallness of daily life without feeling that smallness as a loss. The astronauts who walked on the moon offer some guidance here, imperfect as the analogy is. Several of them found the return to Earth unexpectedly difficult. Buzz Aldrin spoke openly about the depression he experienced after Apollo 11, the sense of anticlimax, the difficulty of finding meaning in ordinary life after the most extraordinary experience in human history. Edgar Mitchell had a profound spiritual experience on the way back from the moon, looking at Earth and the stars simultaneously and feeling an overwhelming sense of universal connectedness that changed his worldview permanently. Alan Bean turned to painting, spending decades trying to capture on canvas what he had seen and felt in a place that no painting could fully contain. Your crew has had longer to process, years longer, and the ship's psychological support structure has been more sophisticated than anything the Apollo astronauts had access to. But the core challenge is the same. How do you live the rest of a human life after you have done the unhuman thing? How do you find the scale of ordinary days adequate after you have stood under an alien sun? The answer: tentative, imperfect, individually constructed by each crew member in their own way, seems to be this: you carry it with you, not as a weight, as a lens. The experience doesn't displace ordinary life, it enlarges it. The grocery store is not diminished by having stood on Proxima B. The cup of coffee in the morning is not less real. If anything, it is more real, because you know now, in your body and your bones, that this specific planet with its specific gravity and its specific yellow sunlight and its specific smell of rain and sound of wind is not the default setting of the universe. It is an extraordinary specific accident of physics and chemistry and time. It is improbable and precious and unrepeatable in exactly this form. The ordinary becomes sacred when you know, really know, not just intellectually, but in every cell of your body, that it could have been otherwise. The sun is clearly visible now in the forward cameras. Not just a star, the star. Bigger, brighter, yellower than anything else in the sky. Recognizably, unmistakably home, Earth is still too far to see as a disk, but in a few months it will resolve. A blue-white point will grow into a crescent, then a half-disk, then the full, breathtaking, impossible blue of a living world, seen from space, the color that astronauts consistently describe as the most beautiful thing they have ever seen. A color that exists nowhere else in the solar system, the specific, fragile, inhabited blue of a planet wrapped in ocean and atmosphere and life. You have seen what worlds look like without it. You know now, from direct experience, how rare that blue is, how hard-won, how dependent on a particular chain of circumstances, the right distance from a stable star, the right mass to hold an atmosphere, the right chemistry to spark and sustain biology, the right sequence of catastrophes and recoveries and extinctions and explosions of complexity over billions of years to produce, eventually, improbably, the kind of creature that builds telescopes and writes music and asks questions about the universe, and sometimes, rarely, expensively, at enormous cost and with enormous courage, actually goes to look. The crew gathers in the observation module when Earth first resolves into a visible disk. No one announces it. Someone just quietly mentions it on the general channel, and within minutes everyone who is off duty has made their way there. They stand together in the cramped space, pressing against the viewport or watching the feed on the screen, and look at the growing blue-white point in silence. Someone cries. Someone laughs softly. Someone says something in a language that only two other people on the ship understand, and the translation doesn't come close to carrying what was meant, but everyone nods anyway. There is still the re-entry to survive, the physical one, the controlled fall through Earth's atmosphere in a vehicle that has been in space for the full duration of the mission and whose heat shield will be tested for the first time since launch. There are still the quarantine protocols, because the samples from Proxima b cannot be brought into Earth's biosphere without extensive containment and verification procedures, not because anyone is certain they carry anything harmful, but because the consequences of being wrong are too significant to risk. The samples go to a dedicated astrobiology facility, purpose-built in the years since your departure, where the most controlled, most sophisticated analysis in human history will begin. And then there is the landing itself, the bump of touchdown, the hatch opening, the first breath of real air, not recycled, not processed, not the same molecules that have been cycling through a closed system for years, but actual Earth air, carrying the smell of the world outside. Several crew members describe, later, that this is the moment they break down completely, not the discovery on Proxima b, not the first step on another world, not the sight of Earth growing in the viewport, but the smell of air, the incomprehensible, unremarkable, overwhelming smell of a planet that is alive, home. But the journey is not finished, not really, because the samples are in the laboratory now and the analysis is beginning. And all the most important questions are still open. Was it life? Is it related to us? Is it an independent origin? Does it tell us we are not alone? Or does it tell us something even more extraordinary? That life is not a miracle but a habit? That the universe makes life the way it makes stars, abundantly and without ceremony, wherever the conditions allow? Those answers are coming, slowly, rigorously, in the way that real science delivers its verdicts. And while we wait for them, while the world holds its breath and the laboratory runs its tests and the data builds toward a conclusion, we need to talk about what this all means. Not just for science, for us, for the whole strange, short, luminous experiment of human civilization, because the journey to Proxima Centauri is not just a story about a star 4.24 light-years away. It's a story about what we are, what we're capable of, what we choose to reach for when we could just as easily stay home and look down instead of up. If you are still watching, you're exactly the kind of person this channel exists for. Make sure to subscribe and give this video a like. Every day we go somewhere new, ask something hard, and come back with a little more wonder than we left with. Now let's ask the uncomfortable question. The one that every mission of this scale eventually has to answer, not to the scientists, not to the engineers, but to everyone else, to the taxpayers and the policymakers and the ordinary people living ordinary lives on a planet with no shortage of urgent, immediate, pressing problems that need attention and resources right now. Why? Why spend the treasure, the intellectual capital, the financial resources, the decades of human effort, the risk of human life, on a journey to a star 4.24 light-years away? Why reach for something so far and so uncertain when there is so much that needs doing right here? When children go hungry, when diseases go untreated, when infrastructure crumbles and ecosystems collapse, and the list of things demanding our attention and our resources never gets shorter? It is a fair question. It deserves a serious answer, not a dismissive one, not a hand-waving appeal to inspiration, but a real, grounded, honest reckoning with what exploration costs and what it returns. Let's start with the practical case. Because it exists, and it's stronger than most people realize, every major technological revolution in modern history has been seeded, at least in part, by basic research that seemed at the time to have no practical application whatsoever. The mathematicians who developed the theoretical foundations of quantum mechanics in the 1920s were not trying to build computers or MRI machines or smartphones. They were trying to understand the behavior of electrons. The engineers who developed radar during the Second World War were not trying to invent the microwave oven. That came later, accidentally, when a researcher noticed that a chocolate bar in his pocket had melted near an active radar emitter. The scientists at Bell Laboratories who invented the transistor were working on fundamental questions in solid-state physics. The Internet grew from ARPANET, a military communications research project that nobody imagined would one day carry the sum of human knowledge to every corner of the planet. This is the pattern. Basic research, the kind driven by curiosity rather than immediate utility, generates the raw material from which practical revolutions are later built. You cannot always know in advance which questions will yield which applications. The history of science is full of straight lines drawn backward through time from world-changing technologies to the apparently useless theoretical work that made them possible. Space exploration follows this pattern precisely. The technologies developed for NASA missions and for the space programs of other nations have generated thousands of spin-off applications that now permeate daily life. Memory foam, originally developed for aircraft cushioning and then used in NASA spacesuits, is now in mattresses and shoe insoles worldwide. Scratch-resistant lens coatings came from research into helmet visors. Freeze-drying technology for food preservation was refined for space missions. Water filtration systems used in developing countries today trace lineage to technologies developed for recycling water on spacecraft. Insulin pumps, portable cordless tools, LED lighting systems, fire-resistant materials, improved air purifiers. The list runs to thousands of items, compiled and published by NASA's own spin-off program over decades. An interstellar mission would generate orders of magnitude more. The propulsion technologies required to reach even a fraction of light speed would transform energy generation and transportation on Earth. The life support systems capable of sustaining a crew for decades in deep space would revolutionize closed-loop agriculture, water recycling, and habitat design for extreme environments here on our own planet. The radiation shielding materials developed for interstellar travel would have immediate applications in cancer treatment, nuclear safety, and protection for workers in high radiation environments. The medical technologies required to monitor and maintain human health across decades without access to hospitals would advance telemedicine and remote diagnostics beyond anything currently imaginable. You do not invest in reaching the stars and receive only stars in return. You receive a civilization pulled forward by the act of attempting the impossible. But let's be honest, Biz. The practical argument, as strong as it is not the real reason, not the deep one, because human beings were exploring long before they could calculate the return on investment, long before they had spreadsheets or cost-benefit analyses or economic models, long before they even had the conceptual vocabulary to frame exploration as something that needed justifying. We explored because we are the kind of creature that explores, because curiosity is not a hobby we picked up, it is a core feature of what we are. The same cognitive architecture that drives a toddler to open every cabinet, taste every object, and ask why, approximately 400 times per day, is the architecture that put footprints on the moon and images of Pluto on our screens, and, in the scenario we've been tracing through this entire journey, eventually put a human being on the surface of a world orbiting another star. We are the animal that imagines. We are the only species on this planet, and possibly in this region of the galaxy, that builds models of the future, that constructs detailed pictures of places we have never been, that feels the pull of the unknown as something closer to invitation than warning. This is not a flaw, it is the trait that got us out of the African savanna, across land bridges into new continents, onto boats crossing open oceans, and eventually off the surface of the planet entirely. Every time our species has suppressed or penalized that curiosity, every era of enforced intellectual stagnation, we have stagnated. Every time we have unleashed it, funded it, celebrated it, we have made leaps that seemed impossible from the starting line. Exploration is not a luxury we allow ourselves after the important work is done. Exploration is part of the important work. It is part of what makes a civilization worth sustaining in the first place. There is a philosopher of science named Carl Sagan. You may know him as the voice behind the original Cosmos television series, or as the author of Pale Blue Dot, who spent much of his career making exactly this argument. Not just that science is useful, but that the scientific perspective, the willingness to ask hard questions, to doubt comfortable answers, to look honestly at evidence and follow it wherever it leads, is essential to the survival and flourishing of a free society. Sagan wrote, in a passage that has stayed with me since I first encountered it, that somewhere something incredible is waiting to be known, that the cosmos is full of wonders that make human pretensions seem small and our possessions pale, but also, and this is the part that cuts deepest, that we are a way for the cosmos to know itself, that the universe through us has become aware of its own existence, that every time a human being looks at the night sky with curiosity rather than fear, the universe is in some meaningful sense looking back at itself. Think about what that means for a moment. The atoms in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, were forged in the cores of stars that lived and died before our sun was born. You are made of star stuff in the most literal chemical sense. When you look up at the sky, stardust is looking at stars. When a human crew stands on the surface of Proxima b and looks back toward our sun, the universe has arranged itself so that a small collection of its own atoms, shaped over billions of years by evolution on a small rocky planet, can experience the scale and beauty and strangeness of what it has made. That is not a small thing. That is, depending on your perspective, the most extraordinary thing imaginable. Now let's talk about the other dimension of why this journey matters, the one that has to do not with technology or philosophy, but with survival. We live on a single planet. Every human being who has ever lived, every person, every civilization, every act of love and cruelty and genius and ordinariness has played out on the surface of one rocky world orbiting one middle-aged star. And that star, like all stars, will not last forever. In roughly 5 billion years, our Sun will exhaust the hydrogen fuel in its core and begin to expand into a red giant, swelling outward until it engulfs Mercury and Venus and possibly Earth itself. Long before that, in perhaps 1 to 2 billion years, the Sun's increasing luminosity will begin to make Earth's surface too hot for liquid water, triggering a runaway greenhouse effect that will transform our planet in ways incompatible with life as we know it. 5 billion years is an almost incomprehensible stretch of time. It is longer than the current age of the Earth. It is longer than the total lifespan of many stars. On the timescale of a human life, it is meaningless as a practical concern. And yet, civilizations think on longer timescales than individuals. Institutions, cultures, bodies of knowledge, ways of understanding the world, these can persist and evolve over thousands of years. And if we aspire to be the kind of civilization that thinks seriously about its own continuity, about the preservation not just of human bodies but of human knowledge and human meaning, then the single planet problem is eventually relevant, more immediately relevant. And this is not 5 billion years away, it is a timescale measured in centuries or less, is the vulnerability of any species concentrated in one place. Asteroid impacts, supervolcanic eruptions, runaway climate change, global pandemics, the risks posed by our own technology as it grows more powerful. None of these are hypothetical. They are documented, recurring features of this planet's history. The dinosaurs were not wiped out because they failed to build a civilization. They were wiped out because all their eggs were in one basket. Literally one planet, one biosphere, one catastrophic impact event, and 66 million years of evolutionary history was erased in geological time, becoming a multi-planetary species, and eventually a multistellar one, is not just an adventure. It is, in the longest view, a survival strategy. It is the way a thinking species backs up its data, and every step we take toward that capacity, every mission, every technology, every generation of engineers and scientists who push the boundary of what's reachable, is a step toward a future in which a single bad day in one solar system does not end the story of consciousness in this corner of the galaxy. There is one more dimension of why this matters, and it is perhaps the most personal, the most human, the hardest to put into words without it sounding like sentiment rather than substance. Exploration changes the explorers, and the explorers change everything else. Every astronaut who has looked down at Earth from orbit has described some version of what the writer Frank White called the overview effect, a sudden, visceral, irreversible shift in perspective. From up there, the borders between countries are invisible. The divisions that seem so solid and so permanent from the ground, between nations, between peoples, between ideologies, dissolve into the simple, overwhelming fact of a single fragile world wrapped in a thin blue line of atmosphere, floating in the black. And once you have seen it that way, you cannot entirely unsee it. The perspective carries back. It informs the way you talk about the planet, the way you think about belonging. Now imagine what happens to a species, not just a handful of astronauts, but a whole civilization, when its reference point expands to include another star. When children grow up knowing that humanity has stood on the surface of another world in another stellar system. When the question of whether we are alone has been answered, one way or the other, not by speculation but by direct investigation. When the cosmic address of our species includes, for the first time, a destination beyond our own solar family, that shift in perspective, The overview effect scaled up to an interstellar overview is not just inspiring, it is civilization-altering. It changes what we think we are capable of. It changes our relationship to this planet, making it more precious, more clearly worth protecting, while simultaneously making our self-imposed boundaries and divisions more obviously absurd. It changes our relationship to the future, making it feel more open, more navigable, less like a wall, and more like a horizon. Here is what I want you to take from this part of the journey. Not a list of practical applications, not a philosophical argument you can deploy in a debate. Something quieter and more personal than that. You are alive at a specific moment in the history of a species that is, right now, in the earliest stages of becoming something it has never been before. The first telescopes were built only about 400 years ago. The first powered flight was barely more than a century ago. The first human in space launched in 1961, within living memory of people still alive today. The first image of a black hole was captured in 2019. The James Webb Space Telescope began returning images of galaxies formed less than 400 million years after the Big Bang in 2022. We are moving fast, faster than any previous generation of our species. And the trajectory of that movement, if you draw it forward with any honest assessment of where our technology and our curiosity are taking us, points toward the stars. You will not live to see the first crewed mission to Proxima Centauri, in all likelihood, neither will I. That mission, if it happens, belongs to people who have not been born yet, who will grow up in a world shaped partly by the discoveries and technologies and cultural shifts that are happening right now, and who will do things we cannot fully imagine because we are standing at the base of the curve, not the top, but you are part of the chain. Your curiosity, the thing that made you press play on a video about a journey to the nearest star, is the same curiosity that builds the telescopes and funds the research and trains the engineers and writes the mission plans. Curiosity is not passive. It is not just a feeling. It is the leading edge of action. Every generation that asks the question passes something forward to the next generation that gets a little closer to the answer. You are part of that, more than you might think. And now, with all of that behind us, we are almost at the end of the journey, but not quite. Because we haven't yet talked about what the data from those samples actually revealed when the full weight of Earth's laboratories was brought to bear on them. We haven't talked about what the scientific consensus eventually settled on. We haven't talked about what governments and space agencies decided to do next, about whether the discovery, or the near discovery, or the tantalizing almost discovery changed the trajectory of human space exploration in the way the people who made it hoped and believed it would. And we haven't talked about Proxima Centauri itself, the star still burning 4.24 light-years away, and what it means that it will be there, patient and ancient and indifferent to our timelines for 4 trillion more years. Long after everything we have ever built has returned to the atoms from which it came. The laboratory is quiet at 3 in the morning. It usually is. The kind of quiet that only exists in places where extraordinarily careful work is being done, where the instruments are running and the data is accumulating, and the humans who built this place and dedicated years of their lives to this specific moment have finally, after months of preparation, reached the point where the results are coming in. The facility is purpose-built, constructed in the years between the mission's departure and its return, specifically to receive and analyze the samples brought back from Proxima b. It sits in a remote location chosen for its geological stability and its distance from population centers, not because anyone is certain the samples pose a biological risk, but because the protocols for handling material from another stellar system demand the most conservative possible approach. The containment systems here make the biosafety level 4 laboratories used to study the most dangerous pathogens on Earth look relatively straightforward. Every surface, every air current, every molecule that enters or leaves the sample analysis area is monitored and accounted for. Nothing from Proxima b touches the outside world until the scientists inside are certain as science allows, that it is safe to proceed. The lead astrobiologist has been awake for 22 hours. Not because anyone required it, because she couldn't sleep, because the sequencing run that began the previous morning is due to complete sometime in this pre-dawn window, and there is no version of her that was going to be asleep when that happened. She is looking at a screen, and the screen is showing her something that, in 31 years of scientific work, she has never seen before. Let's walk through what the full laboratory analysis eventually revealed. Not the cautious, hedged language of an initial mission report. The final scientific consensus, built over years of replication, verification, independent analysis, and the most intensive peer review process in the history of biology. The water samples from the terminator zone of Proxima b contained complex organic chemistry confirmed across multiple independent laboratories on 3 continents. The amino acid homochirality signal, that strong preference for left-handed forms, held up under every form of scrutiny. The enantiomeric excess was real, reproducible, and inconsistent with any known abiotic chemical process at the concentration and specificity observed. This alone would have been remarkable, but it was what came next that changed everything. The polymer analysis, the breakdown of long-chain carbon molecules in the samples, revealed structures that, under the highest resolution imaging available, showed a level of chemical regularity inconsistent with random assembly, not the smooth statistical randomness of abiotic chemistry, where molecules form and break apart according to energy gradients and probability. Something more like pattern, more like sequence, more like, and the word was used carefully, surrounded by qualifications, but eventually used, information. On Earth, the chemistry of life is fundamentally an information system. DNA and RNA store and transmit molecular instructions using a 4-letter chemical alphabet, 4 nucleobases arranged in sequences that encode the construction of proteins, regulate cellular processes, and copy themselves with extraordinary fidelity from generation to generation. The specific letters of that alphabet, adenine, thymine, guanine, cytosine in DNA, are in a sense arbitrary. What matters is not the specific molecules chosen but the principle. That sequences of molecules can carry information, that information can be copied, that copying with occasional errors generates variation, and that variation under selective pressure generates evolution. The structures in the Proxima b samples were not DNA. They did not use the same molecular alphabet. The specific nucleobase equivalents, if that's even the right word, were chemically different from anything in Earth's biochemistry. But the underlying principle, sequence, regularity, the hallmarks of an information-bearing polymer, was present, tentatively, provisionally, with enormous uncertainty still surrounding the interpretation, but present. The scientific community's response unfolded over years, not hours. Papers were published. Other teams replicated the analysis with the remaining sample material, carefully rationed because the total quantity was finite and irreplaceable. Some found the same patterns, some found ambiguous results. A minority, rigorous, credible scientists with legitimate methodological critiques argued that the information-bearing interpretation was premature, that the chemical structures could be explained by non-biological polymerization processes driven by Proxima Centauri's unique radiation environment. This is how science actually works. Not a single dramatic revelation followed by unanimous acceptance. A grinding, iterative, sometimes contentious process of claim and counterclaim, evidence and counter-evidence. until the weight of the data becomes too consistent to explain any other way. It took years. The public, hungry for a definitive answer, found the pace agonizing. But the scientists understood that the cost of being wrong here, of announcing the discovery of extraterrestrial life based on misinterpreted data, would set the field back by decades and potentially destroy the credibility needed to mount a follow-up mission. So they were careful, excruciatingly careful. And eventually, not with a press conference and a banner headline, but with a landmark paper published in a major scientific journal, followed by an independent replication published 3 months later, followed by a formal statement from a consortium of the world's leading astrobiology research institutions, the consensus arrived. The samples from Proxima Centauri b contain chemical signatures most consistent with biological or pre-biological processes. The evidence for a second, independent origin of life cannot be excluded and, on current analysis, represents the most parsimonious explanation for the observed data. Further investigation, including a follow-up sample return mission and ideally in situ biological culturing experiments, is required before a definitive conclusion can be reached, not confirmed, not proven, but most consistent with. And in science, that phrase, quietly, carefully deployed, carries the weight of a revolution. The world did not end. Civilization did not collapse. Religious institutions did not dissolve overnight. This surprises some people who expected either dramatic celebration or dramatic crisis. What happened instead was something more complex, more interesting, and perhaps more true to human nature than either extreme. There was an initial wave, enormous, global, unprecedented in its intensity. Every major news organization carried the story for weeks. Social media bent under the weight of a conversation that crossed every language and every border simultaneously. The images from Proxima b, the red-lit surface, the dark water pools, the microscope images of those ambiguous rounded structures became some of the most widely shared images in human history, alongside the Earthrise photograph from Apollo 8 and the pale blue dot image taken by Voyager 1. Then the wave crested, and what came after was not silence but integration. The slow, deep work of a species absorbing a new fact about itself and the universe it inhabits. Theologians wrote thoughtfully about the implications for concepts of creation and uniqueness. Philosophers published new frameworks for thinking about life as a cosmic phenomenon rather than an Earth-specific one. Artists made work about it, paintings, films, music, literature, that approached the discovery from angles that science alone could not reach. Educators updated curricula. Children grew up in a world where the question of extraterrestrial life was no longer theoretical but evidential, where the nearest star was not just an astronomical object, but a place where something had happened that changed the meaning of being alive. And in laboratories and universities and space agency planning rooms, a new generation of scientists began designing the next mission. Better propulsion, more sample capacity, in situ laboratory capability, the ability to stay longer, go deeper, look harder. Because most consistent with is not enough. The universe demands better than most consistent with, and the people who do this work would not rest until they had it. Here is what the discovery, provisional as it remains, does to the Fermi paradox. Recall the question, if intelligent life is common, where is everybody? The silence of the cosmos has always been the most haunting argument against the abundance of life. But if life arose independently on Proxima b, the nearest star, our cosmic next-door neighbor, in a system we can barely observe from Earth, then the arithmetic changes dramatically. Think about what it means if two independent origins of life exist within 4.24 light-years of each other, in a galaxy that is roughly 100,000 light-years across, containing somewhere around 200 to 400 billion stars. A density of life that includes even 2 examples in our immediate neighborhood implies that life is genuinely common, perhaps extraordinarily common, perhaps as common as stars with rocky planets, which is to say, common beyond imagination. But that brings the Fermi paradox back with renewed force. If life is common, why is the galaxy not visibly full of it? Why have we detected no radio signals, no laser pulses, no megastructures, no unambiguous evidence of intelligence beyond Earth? The discovery on Proxima b, if confirmed, might resolve the Fermi paradox in a specific way, by suggesting that life arises readily, but that intelligence, technology, and the kind of civilization capable of making its presence known across interstellar distances is genuinely catastrophically rare, that the great filter, whatever it is, lies not between chemistry and biology, but somewhere further along, between microbes and minds perhaps, or between minds and the wisdom to survive the technologies those minds create. This is not a comfortable interpretation, but it is an honest one. And it is one that places a particular weight on our own shoulders, the weight of rarity. If we are among the first or the few, or the lucky, then what we do with that luck matters in ways that go beyond our own story. What we do with our civilization, with our technology, with our capacity for both extraordinary creation and extraordinary destruction, matters not just for us, but potentially for a galaxy that may be waiting, without knowing it, for someone to show that the path from biology to wisdom is possible. Let's come back to the ship. Let's come back to the crew, home now, adjusted imperfectly and beautifully to the ordinary world, giving talks at universities and conferences, writing books, raising children, growing older in the way that all human beings do, one ordinary day at a time, carrying extraordinary memories. What do they say when people ask them what it was like? What is the thing they come back to over and over when they try to capture the essence of the experience in words that other people can actually receive? Almost universally, it is not the technology, not the propulsion system or the navigation or the engineering achievements, as breathtaking as those were. It is not even the surface of Proxima b, as life-altering as standing there was. It is something smaller, something that happened on the journey itself in the long dark between stars, when there was nothing outside the windows but the unchanging field of distant lights. It is a feeling of scale, of having genuinely, physically, experientially understood for the first time how large the universe actually is and how small, and how remarkable one human life is within it. Not depressingly small, not insignificantly small, remarkably small, the way a single note is small within a symphony, complete in itself, meaningful in itself, and also part of something so much larger that the note's smallness is not a diminishment but a kind of grace. One crew member, in an interview given some years after the return, put it this way, she said, "I thought going to another star would make me feel less significant, but it was the opposite. Every morning since I've been back, I wake up and I actually know, not just intellectually, that I am on a living planet, that outside my window there is air and trees and birds and other people living their lives, that this specific, improbable, fragile, remarkable world is my home, and I didn't know that before, not really, not the way I know it now. That more than any scientific finding, more than any technological achievement, may be the most enduring gift of the journey, the gift of knowing where you are, really knowing, in the deep, embodied, perspective-shifted way that only comes from having been somewhere else, having crossed the dark, having stood under a different star and turned around to look back at the one that raised you. The data is still coming in. The analysis is still running. The debate is still alive in the journals and at the conferences and in the quiet conversations between researchers who are absolutely certain of nothing and absolutely committed to finding out. The follow-up mission is in planning, years from launch, decades from arrival, but real. The funding has been secured. The engineering teams are working. A new generation of people who grew up knowing that the nearest star has been visited, that a human boot has touched its planet's soil, are designing the next chapter. And Proxima Centauri is still out there, 4.24 light-years away, burning red and patient and ancient, its stellar wind sweeping across the face of a small world in the twilight zone, where thin water lies in pools on ancient rock, and something we found there, something that might be the second story the universe has written in chemistry and time, waits for us to come back and read it more carefully. The universe is not finished with us yet, and we are not finished with it. Here we are, the last leg, and I want to start it differently from all the others, not with a fact, not with a scenario, not with a physics concept or a mission timeline or a chemical analysis. I want to start it with you, right now, wherever you are, whatever room you're sitting in, whatever time of day it is, whatever is happening in your life outside of this video. You are on a spacecraft, a real one, not a metaphor, not a poetic flourish, a literal spacecraft hurtling through space at approximately 30 kilometers per second as it orbits the Sun, which is itself moving at roughly 220 kilometers per second around the center of the Milky Way, which is moving at around 600 kilometers per second toward the Great Attractor, a massive concentration of matter hundreds of millions of light-years away. You have never, for a single moment of your existence, been stationary. You have been in motion through the cosmos since before you were born. You are a passenger on a planet that is also a vehicle, inside a galaxy that is also a vehicle, inside a universe that has been expanding outward from a single point for 13.8 billion years. You are already out there. You've always been out there. The journey to Proxima Centauri doesn't begin when the engines fire. It began for you the moment you came into existence on this particular rock, in this particular stellar system. What we've been tracing through the last 9 parts of this journey is not a story about going somewhere strange. It's a story about understanding where we already are. Let's take stock of what we now know. We know that the nearest star to our Sun, Proxima Centauri, sits 4.24 light-years away. That's roughly 40 trillion kilometers. A distance so large that the fastest spacecraft humanity has ever built would take tens of thousands of years to cover it. That even traveling at 20% of the speed of light, a target that pushes the absolute boundary of anything remotely near our current technological capability, the journey takes more than 20 years each way. We know that the physics of getting there is formidable but not forbidden. Breakthrough Starshot has demonstrated the serious scientific credibility of laser-propelled light sails. Nuclear pulse, fusion, and antimatter propulsion concepts all exist within the laws of physics as we understand them. They are engineering challenges, not physical impossibilities. The timeline for achieving them is uncertain, but the direction of travel is clear. We know that time itself bends in ways that become significant at high fractions of light speed, that a crew moving fast enough would experience the passage of time differently from the people they left behind, and that this is not science fiction but confirmed physics measured here on Earth with atomic clocks and GPS satellites every single day. We know that the human body is both the greatest asset and the greatest vulnerability of any crewed interstellar mission. That radiation, bone density loss, cardiovascular change, psychological isolation, and the simple biological fact of living for decades in an enclosed artificial environment all pose challenges that serious researchers are actively working to solve. That none of these challenges are categorically insurmountable. We know that Proxima Centauri is not a gentle star, that it is a red dwarf that flares with extraordinary violence, erupting in ultraviolet and X-ray bursts that dwarf anything our own Sun produces relative to the planet in the habitable zone. That Proxima b the rocky exoplanet orbiting in the zone where liquid water could theoretically exist, is tidally locked, one face permanently lit, one permanently dark, and experiences a radiation environment that makes the concept of surface habitability genuinely uncertain. We know that the search for life is real science, not wishful thinking. That biosignatures, chemical fingerprints of biology, readable in the light that passes through a planet's atmosphere, are being searched for right now with real telescopes using real instruments. That the James Webb Space Telescope is already doing early versions of this work, that a ship in orbit around Proxima b could do it with a precision and confidence that no Earth-based telescope can match. And we know, or we traced, carefully and honestly, in the spirit of following evidence wherever it leads, that in the scenario we explored, the samples brought back from the terminator zone of Proxima b carried chemical signatures that the scientific community eventually concluded were most consistent with biology or pre-biology, not proof, not certainty, but the kind of evidence that shifts the probability and changes the question from "is there life out there?" to "when will we know for sure and what do we do next?" All of this is real, the distances are real. The physics is real, the biology research is real, the mission concepts are real, the exoplanet is real. The water in the terminator zone is a real scientific possibility based on real climate models. The only fictional element in this entire journey has been the crew, the specific human beings we imagined walking on that surface, running those samples, composing that message home. The rest of it is the universe, described as accurately and honestly as current science allows. Now let's talk about what you do with this, because knowledge is not an end point. It is a beginning. The first thing you can do is look up. This sounds absurdly simple, and it is also more powerful than most people give it credit for. On a clear night, facing south if you are in the northern hemisphere, you can find the constellation Centaurus, or its brightest stars at least, since the full constellation dips below the horizon for most of the northern latitudes. Alpha Centauri, which includes Proxima Centauri's companion stars, appears as the third brightest star in the night sky, a beautiful yellowish-white point that has been visible to human eyes for as long as human eyes have existed. Proxima Centauri itself is too faint to see without a telescope, a reminder that the nearest star to a sun is still in the visible spectrum, barely there. But knowing it's there changes the looking. When you stand outside on a clear night and face that part of the sky, you are looking at a real system. A real star with a real planet in its habitable zone, where real water might pool in the eternal twilight of the terminator, where something might be alive right now, at this moment, having never heard of us and never knowing we exist and never knowing that one day a small collection of atoms from a distant blue world will cross the dark to visit. That thought, held seriously, not casually, is one of the most perspective-altering experiences available to a human being without a spacecraft. The second thing you can do is follow the science, not in the passive, occasional, "I'll read an article if it trends" way, but actively. The search for extraterrestrial life is happening right now. The James Webb Space Telescope is making discoveries. The Nancy Grace Roman Space Telescope, designed for wide-field infrared surveys, will extend our catalogue of exoplanets and atmospheric candidates in the coming years. The extremely large telescope, currently under construction in Chile's Atacama Desert, with a primary mirror 39 meters across, will, when completed, be capable of directly imaging nearby exoplanets and analyzing their atmospheres with unprecedented detail. It may, within the next decade or two, give us our first real spectroscopic look at Proxima b's atmosphere from Earth. These are not distant, hypothetical instruments. They are being built, they are being funded. They are staffed by thousands of researchers who got up this morning and went to work on exactly the questions we've been exploring in this video. Following their work, reading about their findings, sharing their discoveries, understanding what they're looking for and why, is a way of participating in the search without leaving your chair, and participation matters. Public engagement with science shapes science funding decisions, educational priorities, and the cultural value placed on the work of discovery. You are not a passive audience for the greatest story ever told. You are a stakeholder. The third thing, and this is the one that I think matters most, is to carry the perspective. We talked in Part 8 about the overview effect, the shift in perspective reported by astronauts who looked down at Earth from space and saw, for the first time, a single fragile world without borders. We talked about how the interstellar version of that effect, the shift that comes from understanding our place in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, most of them hosting planets, at least some of those planets potentially hosting life, might be civilization altering if it were genuinely, widely shared. Here is the thing, it can be. Not through spaceflight. Most of us will never leave this planet, and that is fine. But through understanding, through the specific kind of imaginative engagement with the actual scale and structure of the cosmos that science makes possible. Through looking at a night sky, not as a decoration but as a map. Through knowing that the light reaching your eyes from Proxima Centauri left that star more than 4 years ago, before it began its crossing of the dark, before it traveled 40 trillion kilometers, before it entered Earth's atmosphere and passed through the lens of your eye and activated the cells in your retina and became, finally, a perception in a conscious mind. You are the end point of a journey that began 4.24 light-years away. Every time you look at that star, every time, that is the overview effect available to you right now, tonight, for free, without a rocket. Let's talk about the future honestly, not with false optimism, not the kind that papers over real obstacles with enthusiasm, but with clear-eyed, evidence-based hope. The kind that looks at history and notices a trend. In the last 100 years, humanity went from first-powered flight to the moon, from horse-drawn carriages to electric vehicles, from telegrams to instant global communication, from knowing of 0 exoplanets to having confirmed over 5,000, from having no idea whether the universe had a beginning to measuring its age at 13.8 billion years with reasonable precision, from understanding nothing about the structure of DNA to editing the genome of living organisms. The curve of human capability, when you plot it honestly over time, is not flat. It bends upward, it accelerates. The tools we will have in 50 years are as hard for us to imagine as smartphones were for someone in 1973. The discoveries we will make in a century are as unpredictable as relativity was to a physicist in 1880, and the missions we will launch in 200 years, the actual hardware, the actual people, the actual crossings of actual interstellar distances, may make everything we currently imagine about reaching Proxima Centauri look the way a hot air balloon looks next to a spacecraft. We are early, embarrassingly, thrillingly early. We are the generation that is building the foundation for things we will not live to see. The way the people who laid the first transatlantic telegraph cables were building the foundation for the internet. What we do now, the curiosity we sustain, the science we fund, the education we provide, the cultural value we place on asking hard questions and following evidence honestly, determines what becomes possible later. You are not watching history from the outside. You are inside it, right now, at one of the most consequential moments in the story of an intelligent species, learning what it is and where it lives and what it might become. Here is what I want to leave you with. Not a summary, you've done the work, you don't need a recap. Not a call to action exactly, though action matters. Something more fundamental than either. There is a version of your life in which the scale of the cosmos is paralyzing, in which 4.24 light-years feels like an accusation, a reminder of how small and brief and inconsequential one human life is against the backdrop of a universe that has been expanding for 13.8 billion years and will continue expanding for trillions more, in which the silence between stars feels like loneliness rather than possibility, in which the difficulty of the journey makes the reaching feel pointless. I understand that version. I've felt it. Most people who think seriously about the cosmos have felt it, that specific vertigo of scale, that momentary dissolving of significance. But here is the other version, the one that I think is truer and more useful and more aligned with what the evidence actually suggests. You are made of atoms forged in stellar cores. The iron in your blood was made in a supernova explosion. The carbon in your DNA was cooked in the heart of a dying star. You are not separate from the cosmos, looking at it from the outside. You are the cosmos looking at itself from the inside, with curiosity, with awe, with the capacity to ask questions and build instruments and follow evidence and care about the answers. The fact that the universe is vast does not make you small. It makes the fact of your consciousness, your specific, improbable, temporary, unrepeatable consciousness, extraordinary. You are what happens when the universe arranges matter in a sufficiently complex way that it becomes aware of its own existence. You are 13.8 billion years of physics and chemistry and stellar evolution and planetary formation and biological evolution, and all of that complexity has produced, among other things, a creature that watches videos about journeys to other stars and feels something in its chest when it thinks about standing on the surface of another world under a red sun. That feeling, that tightening in the chest, that mixture of longing and wonder, and something that might be called recognition, that is not a distraction from the important things in life. That is one of the important things. That is the part of you that is most fully human. The part that looks at the horizon and wonders what's beyond it. The part that built the first boat and pointed it at open water. The part that will one day, not you, but the unbroken chain of curious creatures that runs through you, point a ship at a star and go. Proxima Centauri is 4.24 light-years away. It has been there, burning red and patient, for nearly 5 billion years. It will be there, still burning, for 4 trillion more, long after our sun has exhausted itself, long after this planet has been transformed beyond recognition, long after the particular arrangement of matter that constitutes human civilization as we know it has evolved into something we cannot yet imagine. And somewhere in the terminator zone of the rocky planet that orbits it, in the thin pooling of liquid water on ancient stone, in the chemistry that hums quietly in the eternal red twilight, something may be happening, something small, something microscopic and slow and utterly indifferent to our timelines and our questions and our yearning to not be alone in the universe, or nothing may be happening. The pools may be barren, the chemistry may be abiotic, the universe in that particular neighborhood may be empty of biology in any form. Either answer is extraordinary. Either changes something fundamental about how we understand our place in the cosmos. Either answer is worth crossing 40 trillion kilometers to find, and that is, in the end, the whole story, not the propulsion systems or the time dilation or the radiation shielding or the sample analysis or the political debates about funding. The whole story is this: there is a star, there might be life there, we don't know, and not knowing, for our species, is not a reason to stop. It is the reason to go. It has always been the reason to go. Thank you for making this journey with me. All the way out, to the edge of our stellar neighborhood, and all the way back, through the physics and the biology, and the psychology, and the philosophy, and the long, beautiful, humbling dark between the stars. If this video changed the way you look at the night sky, even slightly, even for a moment, then it did exactly what it was made to do. Now go outside tonight, find the south. Look for the stars of Centaurus if you can, and actually know that one of those points of light is the nearest sun to our own, that it has a planet, that water might pool there in the red twilight, that we have built telescopes aimed at it and spacecraft concepts designed for it and entire careers dedicated to understanding it, and that one day, if we are patient and curious and brave enough, someone will go. Maybe someone who is alive right now, somewhere on this planet, watching a video, feeling that tightening in the chest, maybe someone exactly like you. The stars are not going anywhere, and neither, it turns out, are we. But the video showing on the screen right now is exactly where your brain needs to go next. We explore why deep space gets more terrifying the further you go. We just crossed 4 light years and made it back, but the further into deep space you venture, the less the universe resembles anything familiar. I will meet you in that video.